Hey, good afternoon. Here we are. It's Tuesday, and it's a Riedel Tuesday. Thank you for letting us borrow that phrase today. Our friends at Riedel have loaned Stephen to us for this afternoon to talk about the exciting topic of SMPTE 2110. You know, if I would have told you 4 weeks ago that I would be using that very phrase, I would not have believed it. But you know what? Guess what? We're here, and I am really, really pumped. This is probably one of those webinars that we've done where I've been really excited about it because it's bigger than any one thing. You know, if we talk about AES 67, we're talking about SMPTE 2110. If we talk about Dante, we're talking about SMPTE 2110. But that's just a fraction of what that really encompasses. So today, this is a big, big topic. So I'm just going to tell everybody right up front. Stephen's done a great job of pulling together the basics and the complex. You're going to walk out with more questions than you came in with. I'm just going to tell you that right now up front, and I feel very good about that. To me, that's the mark of a great topic, is when it causes us to think differently and to consider what is our world going to be. Well, SMPTE 2110 is probably as future looking as today, right? It's not future looking, it is today, but it's also going to be for the future. So I see we have our attendees joining us. We got about 90 folks online so far, so that's a good audience still coming in. We'll let everybody continue to join. But while we're waiting, Pete, Mac, good afternoon. It's good to see you guys.
Good to see you. I hardly ever see you anymore.
I know, I feel like, you know, I'm not really sure what's going to happen when that day comes and I got to phone in and go, hey, you know what? I got to go to work today, so I'm not going to be on with you. It's going to be an awkward moment, I'll be honest.
Trust me, it is awkward because I've had to do that a couple of times.
You know that feeling, right? But you take it, you know, we're all going to take this to work with us, and that's all good. I certainly take my work home with me every night, so and I'm proud of that. But let's talk about Q&A today, because this one, like we said, it's going to have a lot of questions around it.
I'm sure
we're not
it will.
going to get to them all.
Yeah.
But let's talk about how we're going to collect them and how we'll, you know, and getting that passed on to Stephen and back up on the website.
Sure. A lot of people will know how we collect them, but I think this is an exciting topic. It's as we've all mostly conquered audio over IP with the spread of Dante, and we've embraced Dante and embraced audio over IP. The future is also going to blend in video over IP, and 2110 is the SMPTE spec that's going to help us get to the point of video over IP and the co-joining of audio and video together over the same network. And I think this is going to be a really interesting topic.
So and a much more unified method, by the way. I think that's the key, right? This is about the unification of all our disciplines.
And it's applicable even before video joins in with AES 67.
Mm-hmm.
It's pretty much required for AES 67. So there is a question section on the GoToWebinar control panel that's on one side of the screen or the other. Mine's always been on the left till today, when suddenly it's on the right. You can open up the little pull down for questions and type in your questions there. We will likely not be able to get to all the questions, but we will get to as many of the individual questions as we can and try to cover the topics of all the questions. And yeah, we'll continue that right up until we run out of time, which is usually well after we thought we would run out of time.
Pete, you got any thoughts on this one?
Well, I want to say hello to my friend Brew, who is an avid Riedel fan, but also want to mention that I'm sure within 10 years, some pharmaceutical company is going to provide a a new pill that has SMPTE 2110 in it, and you just take it, and your whole body is networked. I'm sure that's coming any day now.
Any day now.
Any day now.
Stash
So
99, actually.
exactly. So take it away.
All right, we'll leave it to you, Stephen. And handouts are waiting for everybody. I know everybody cares. So, Stephen, thanks, buddy, for being with us. I'm going to click off now and listen closely.
Sweet. All right. So we're going to start off kind of going through some IP basics to kind of get a foundation to start talking about SMPTE 2110 with. We're going to kind of dive a little bit deeper into that. It's going to be kind of a broad overview of a CCNA, and by broad, I mean very, very broad. And we're going to start that off by talking about the OSI model. You guys have most likely heard about the OSI model before. It consists of 7 parts: physical, data link, network, transport, session, presentation, and application. So what that basically means for us is that when we look at the application layer, we're looking at high-level APIs, resource sharing, remote file access. We're looking at all the stuff that we tend to see as users on maybe our computer. This is kind of what makes up our user experience for everybody. The presentation layer is basically what takes all of the application layer, what we're used to seeing, and it transitions that into the next layer down, the session layer. This is where we see a lot of compression and encryption. A lot of security is in this. And then that leads down into the session layer, which is where we manage our communication sessions. This is kind of where we say we have like one node saying hello and the other node saying, yes, hello, I'm part of this session as well. And that's kind of that talk back and forth. Then we start to get into the stuff that's all really interesting to all of us, and that's the transport layer. So this is how we actually look at data on the network. We look at it in terms of packets, in terms of segmenting, and how it goes from point A to point B, and the method that it's decomposed on one side and emitted into the network on the other side, right? So, and then that moves into the network layer, which is how we structure and manage our network. It includes addressing, specifically logical addressing. It includes routing and traffic control. So those are really big key parts of our network that we have to keep in mind. And then we get down into the more nitty-gritty stuff, the data link layer. So this is the reliable transmission of data packets and frames between two things on a physical layer. So this starts to get closer to that physical ones and zeros electrical impulses that we're looking at on the network side. And then of course, we have the physical layer, the transmission and reception of raw bits and streams over a physical medium. So that's as physical as it gets. That's as ones and zeros as it gets for us. And if we're going to kind of break that down a little bit more, and we're going to go from the bottom up now. We started from the top down. Now we're going to go from the bottom up. So when we talk about our physical layer, our layer 1, and this is often you'll hear people refer to layer 1 problems. That's our physical layer problems, cabling, ones and zeros, all that kind of fun stuff. So this is where the digital bits and bytes, those are converted into electrical impulses. So our physical could be Cat5, our physical could be coaxial, whatever it works for us, whatever is the method that we need to transport things over a cable, that's how we're going to do it here. And this happens on the network interface card. This isn't something that happens in the operating system. This happens at the physical layer on our cards that are in our computers on the network interface. It's on all of our Riedel gear or our network switches, all that kind of stuff. And then we've got our data link layer. So the data link layer more in depth provides node-to-node data transfer. It provides a link between two directly connected nodes. So if you have a cable connected from one thing directly to the other thing, most of that communication is going to happen through data link. It's not going to happen on the layer 3. It's not going to be routed. It's going to be data link layer. A lot of error correction actually happens at the data link layer. So when we see issues with ones and zeros being corrupted, a lot of the error correction that's built into a lot of these standards actually happens on the data link level. Data link provides the protocol for flow control, and this also happens at the network interface card. So this is also pretty physical. This happens not in the operating system, not in those processors, but in the chipsets on the actual card, on those connections. And then we talk about networking, continuing to move up to the list, to layer 3, the network layer. This provides functional and procedural means of transferring packets from one node to another. That means instead of just sending a packet to another person, this is a little bit more structured. This is how we get packets from point A to point B when it's not as simple as a cable connected from one thing to the next thing. Every node has an address which permits other nodes connected to it to transfer messages. So that's what we're talking about when we talk about logical addressing versus maybe non-logical addressing, something that we can all remember. And this lets the network find a way to deliver messages to a destination node. So this allows the switch to kind of take control of how packets are being transferred between point A and point B, right? This is where things start to change between the network interface card and the operating system. Now, the operating system is kind of managing a lot of the things that happen on what we call layer 3 networking. Moving up still, we've got our layer 4, our transport layer. So this controls the reliability of a given link through flow control, segmentation, and error control. So while a lot of the physical error control and error fixing happens on the data link layer, on the level 2 layer, the more operating system side of that happens at the transport layer. So this is where we talk about the difference of like how our packets are split up. Are they split up 1, 2, 3, 4, or is it a little bit more complex than that? Is it a little bit more fluid than that? The transport layer can keep track of the segments and retransmit any that fail delivery. And we're going to talk about that a little bit later and like why that's important and how that happens. It provides acknowledgements on successful data transfer. So again, that's part of that failure to deliver and like retransmittance and all that kind of stuff. And this again also happens at the operating system level. This doesn't happen at the switch level. It doesn't happen at the network interface card level. This actually happens at each of the hosts. So that starts to encode and decode at your computer or at your antenna or at your network device or your server. Then we start to get into layer 5, 6, and 7, which are important, but a little bit less important to what we're going to see in our daily lives, kind of dealing with SMPTE 2110, right? So this is where we establish and manage and terminate connections. This is the session layer. So this is saying, hey, I'm peer 1 over here, I'm peer 2 over here. We're going to create a session and talk to each other through this session that we're going to create. Then we have the presentation layer, which basically takes everything on the session layer, that TCP data or that UDP data, it takes all of the network information, and it takes that and transfers it into the application layer for us so that we can use it in applications like a browser or something like that. And this often has compression functions built into it. So normally when you're sending data from a host on one side of the world to a host on the other side of the world, a lot of the compression happens in what we call layer 6, the presentation layer. And then finally, we have layer 7, which is our application layer. That's the layer that we're all going to be most familiar with in terms of using things. Excuse me. So this is kind of where name resolution works. So DNS, this is where email lives. This is where HTTP lives. So when you go to a website, that's all application layer kind of stuff. So you say www.google.com, that's application layer. When it comes back to you and you see google.com in your browser, that's also application. If there's information that you guys feel like you're missing in the OSI or there's things that you don't understand, there's a bunch of good videos online about this. But this link is actually in the handouts that you have. If you want to go to that link, and it explains in a very simple way the OSI model, kind of walks through a lot of that stuff if there's any review that's needed there. So again, let's talk about real world applications for all of these things. Layer 1 is our physical layer. So that's our Cat5 cable, as simple as that. That's through the messages that are being transported, right? So when people say, oh, I have a layer 1 problem, typically that's because there's an air gap or someone cut a cable or there's just not a cable there. That's kind of what a layer 1 issue looks like. Now, when we talk about layer 2, this is the stuff that starts to get a little bit more interesting. It's not just the physical ones and zeros. This is the transport of a message between host A and host B without major recipient data, right? So if I have a note and I know that I want to pass it to Kelly, I'm going to pass that note to Kelly. It doesn't really matter where he lives. I just know his name, and I'm going to pass that to him and give that directly to him, right? And that's very different than our layer 3, which is our network layer, the transportation of a message from A to B with recipient information, right? So with recipient information, I can't just give a letter to Kelly. I actually need to address the letter and send it to his address so that he gets it, because right now we're not in the same room with each other. We're actually halfway across the globe. So if I need to send a letter to him, I'm going to actually address it to him and send it over to his address. And that's kind of the correlation between layer 2 and layer 3 addressing and messaging schemes. And when we talk about layer 4, things start to be a little bit different. It's not so much how messages get to where they need to go and the addressing scheme in which, but it has to do with more how they're sliced up and packetized. So we are looking right now at this layer 4 section. And really what we deal with on a day-to-day basis is, in terms of layer 4, is TCP versus UDP, right? So TCP is a method of breaking down packets and information in a way where we have really small packets and they're sent individually over one route or many routes at the same time, and then they're reassembled at the receiving end. And the ability to recover automatically from failures is built into that transmission method, right? So what happens is, if I'm a TCP sender and someone else is a TCP receiver, I'm going to say, hey, do you want this packet? And they're going to say, yes, I want this packet. And I say, all right, great. This packet is 128 bits. And that person says, okay, got it, 128 bits. And then I say, are you sure you want it? I said it was 128 bits. You want it? And they say, yes, I definitely want it. And then I send it. And then I say, hey, did you get my packet? And they say, nope. And I say, oh, crap. All right, so I'm going to send that again. And so I take that packet and I start the whole process over. And then when they receive it and they send me, yep, I got the packet, then we start all the way over with a new packet and continue moving on from there. So it's very slow, but it's very methodical, and it'll always work because there's that retransmission built in. There's basically a way to recover from packet loss, a way to recover from jitter, and all that kind of stuff. So this is very different than UDP, which is very fast. It's very real time. There's no overhead that talks about, okay, well, do you have it or not? Okay, UDP doesn't care. So the UDP uses a simple transmission without any handshakes to reliably order and send data across the network. Like I said, this is real time, so this is why a lot of the things that we use in terms of live audio over IP, that's why it uses UDP, is because yes, TCP has all these built-in redundancy features, but it's so slow and so small that you can't get all that information through in a timely manner. So it's based off of, instead of TCP, where it's based off of IP addresses, source and destination IP addresses, typically UDP is based off of source and destination ports. So that's why when we talk about UDP ports, that's kind of what we're talking about here. And typically UDP is multicast, because that's why we're using UDP, is because a TCP session is from source to destination, and then from source to another destination, from source to another destination, where UDP sends the packet out. Doesn't matter where it goes, it just needs to be received by somebody. So that's layer 4. So those are the main OSI layers that we're going to talk about today. That's what we're going to dive deep into. We're not going to really dive deep into session application and presentation layers, because that's not nearly as important and prominent in our world in terms of troubleshooting, in terms of understanding 2110 as these are. So let's go back to layer 2 and talk a little bit more about addressing and how that works, and more of what you would see in the real world, right? So this is a phone that I had set up a little while ago. This is its address page, and we'll see that I basically have a MAC address associated with that phone. It's connected to my Wi-Fi network in the house. and its MAC address is 4040A7BBDF5E. So that's a hexadecimal MAC address, and it's made up of two parts. The first part is the OUI, the organizationally unique identifier, and the UAA, the unique address assigned by the vendor, right? So those are all associated, those are all assigned by the IEEE. The IEEE basically sells the start of MAC addresses to a bunch of different organizations. So that means that if I have 4040A7, I can actually look up what 4040A7 means, what company that belongs to. And so that actually, if we look at my list of MAC addresses here, I can actually look that up and say, oh, okay, 4040A7 is actually Sony mobile communication phone. So that's what was connected to my network at that time, was a Sony phone. And if you look, all of these being completely unique organization identifiers, we can actually see Riedel Communications has its own unique identifier. So that's 00197C. So if you ever see that in a MAC address tree on a switch, you know that that's Riedel's. And it's the same thing with all of these. You will never see two of the same MAC addresses on a network, or you shouldn't ever see. Obviously, those bad things happen, but that's part of the IEEE standard, is that everything is completely unique. And that's why layer 2 addressing isn't logical. So when we talk about logical versus non-logical addressing, MAC addresses, while they're really great and they provide a unique address for every single device on the network, it's not a logical way to address things. So let's just take a look at kind of how MAC addresses work in a switch environment, right? So if I have a switch MAC address table, and I basically, I'm looking at the switch MAC address table for this switch right here, and I'm going to try to send a packet from L2 to L6. And when I do that, L2 doesn't know the MAC address, or L2 does know the MAC address of L6, but the switch doesn't know the MAC address of L6, and it's trying to send it to L6. So what L2 is going to do is it's going to go ahead and send its packet out to the switch, and the switch is going to go, okay, I've received that. I don't know where that MAC address is on the network. So what I'm going to actually do is I'm going to send that out to every other host that's on the network. I'm going to send it to L1, L3, L4, 5, 6, and 7. So what happens at this point is that L1, 3, 4, 5, and 7 actually just discard the packet. They don't send anything back to the switch at all. They just say, oh, not mine. And L6 sees it. It says, that's mine. And it sends a packet back to the host at the other side. So it sends it to L2. And the minute that packet goes back into the switch right here, the switch records what the source MAC address for that packet is, and it says, okay, now I know that is this is the host that's associated with this fast Ethernet right here, and so now it will never send another broadcast message that it's trying to send to C49D, whatever. So now, because it knows the destination MAC address of L2, it's going to send it right to L2 and not broadcast it out to the rest of the network. So you only see broadcasts in a layer 2 scenario when the switch is like, I don't know where that MAC address is, who has that MAC address, and it goes out to everybody. I see a question that says, just really quickly, because it pertains to this, is what happens if a MAC address is edited by a user? There was at one point an editable MAC address in Artist. That is true. A long while ago, when the CPU cards for Artist CPUs were being manufactured, they actually had what was called a software-defined MAC address. It's not necessarily illegal against the IEEE to do this, but it can be really bad for a network, because if you format a card and say edit the MAC address, you can basically, if there's duplicate MAC addresses, it really causes a lot of issues with the switch. So that's something that, again, like you said, that's like, it's illegal for the IEEE, but it does happen. That's actually since been rectified, and now that is a firmware-based MAC address. So each one of those MAC addresses is not customizable anymore. That option stays open in Artist for older CPU cards, because if you got an older CPU card and it defaulted to a MAC address that you didn't want to use, then you could change it back to a MAC address that you do want to use. So that's kind of why that option still remains within Artist. Okay, so this is kind of layer 2 addressing. It's really, like I said, non-logical. It's not super helpful to be like, oh, I remember my MAC address off the top of my head, because that doesn't really help us, right? But what does help us is understanding a little bit more about layer 3 and logical addressing. So when we talk about layer 3 and logical addressing, we're talking about IP addresses, and the thing that goes along with an IP address, which is the network mask, the net mask, or the network mask. And all of these are governed by not the IEEE, but IANA, which is the Internet Assigned Numbers Authority. So that's who kind of assigns a lot of these numbers and a lot of this information. So when we talk about IP addressing, we have 3 main classes of IP addresses, and that is Class A, Class B, and Class C addresses, which we'll start talking about in a little bit more depth in a moment. And then there's also Class D and Class E, but we're not going to specifically talk about Class E today. We will talk about Class D, because that's multicast. But first, let's talk about what a subnet mask is to an IP address, because a lot of times it's kind of hard to understand, and it's just a number that's not really explained. So if you notice here, this 255 right here, 255.0.0.0. We'll talk about the 8 in a little bit. Don't worry about that right this second. That actually means that this whole section and this whole section, in relation to these IP addresses, is being blocked out to be used as the network address. The other section of this not blocked out part, can be used for host devices. So this would be considered my device ID, and this over here would be considered my network. So most of us are very used to seeing 255.255.255.0. That's a very common network mask to see. And what that means is that everything here is the network address, which means that can't really be changed, and all of the devices talk to each other on a layer 2 VLAN. But as long as this section stays the same and this section changes, all those devices can talk to each other. So for example, if I have a 192.168.42.1 and a 192.168.42.100, those devices are going to be able to talk to each other if the network mask is 255.255.255.0. However, if I have 192.168.43.1 and 192.168.42.1, those two devices are not going to be able to talk to each other in a layer 2 VLAN. They're not going to just be able to just magically chat with each other. And we'll dive a little bit deeper into that, but I just want to go over the fact that these sections of addresses are actually called Class A, Class B, and Class C, and Class Ds. So Class A is actually a whole section of addresses from 0, 0, 0, 0, 0 to 127.255.255.255. That whole section are 127 Class A networks that can be divided up in any way that you would like. Class B is 128.0.0.0 to 192.255. And those are all able to be divvied up again, same exact way. And then our Class Cs are 192.0.0 to 223.255.255. So these are just blocks of addresses that were basically set aside by IANA to be sold off to corporations. So you'll notice that, like, typically at home, you'll only see a couple different types of IP addresses, but if you go to Google, which is 8.8.8.8, and that's actually their DNS address. So you always know if you're connected to the internet, if you can ping 8.8.8.8. And that is part of a Class A address that Google purchased a long time ago. And then of course we have Class Ds, which don't necessarily have a network mask, and that's 224.0.0.0 to 239.255.255.255. Sorry, give me one moment. All right, so let's talk a little bit more about these network masks really quickly, and then I see a message specific. I see a question specifically related to Class Cs. So if we're talking about network masks, if I have what's called a 24-bit network mask, which is 255.255.255.0, then I will have a possibility of having in that network 254 devices. So if we remember back to our example, 192.168.42.1 onward at a 255.255.255, what that means is anything from 1 to 254 after the 42 can talk to each other. So that's 254 devices in that network. They can all talk to each other. And I can actually break all of my Class C networks up into a possibility of 2 million possible networks, right? Now my 255.255 or my 16-bit networks, my Class Bs, instead of 254, I actually have 254, I think to the power of 254, so that's 65,000 devices in 16,000 possible networks. And it kind of goes up from there. So in a 255.0.0.0, which is an 8-bit, I have 16 million possible devices that can all live on the same 8-bit network, but I only have 126 networks that I can work with there. So when we talked about the slash 8s, the slash 16s, the slash 24s, or the 8-bit, the 16-bit, or the 24-bit addresses, we won't really get into subnetting, and because that's a very large conversation that I think can best be served over a longer period of time talking about it. But basically, each of these addresses is a 32-bit address. 8 bits here, 8 bits here, 8 bits here, 8 bits here, right? So if I mask out 8 of these bits and say, you can't use these 8 bits for your hosts, you can only use it for the network, then that would be an 8-bit network mask, because that means that I have the rest of the 24 bits to play with for my hosts. 8 bits for the network, 24 for the hosts. In a 16-bit net mask, same exact thing, it's just a little bit different. So I've got 16 bits blocked off that I can only use for my network. And then I have 16 bits that I can only use for my hosts. And so I can't, up to that point. So if I basically say in this network, anything with a 128.168 can talk to each other. The minute I add a 128.169, then those two things can't talk to each other without what's called a gateway. And we'll talk about that in a second. And then it's the same sort of thing for a 24. Anything with this section can talk to each other. 192.168.42. I've got 24 bits masked off that says you can't touch these. This is for the network only. This is not for the hosts. And I have 254 hosts right here. And that's kind of how that masking works. So if I say /24, I'm saying 24 bits are all popped in here. And if I'm saying /16, I've got 16 bits all packed in right here, 8 bits all packed in right here. So let's talk about reserved IP addresses, because in a home network, typically if you've got your Wi-Fi router back in the back, it's going to give you what's called a Class C IP address. So you typically get like a 192.168.1.1, right? That's what you get when you connect to your Wi-Fi router at home. And then there's a couple other, these are called reserved IP addresses. They're reserved because they're reserved for private use. So in Class A, The entire 10 dot is reserved only for private use. That means that you will never see a 10 dot on the internet. If you go out to the internet, it's not going to be a 10 dot, it's going to be an 8 dot or a 9 dot or something, but 10 dot is off limits for use on the internet. In fact, most firewalls are set to block any sort of 10 dot coming in over the you can block any sort of 10 dot coming in over your public network, because there's something that comes into that basically saying, hey, don't allow any what's called bogan or bogon networks to come into the thing, any reserved networks to come in, because typically that's like a hacking attempt. So the reserved classes are class A, which is 10.0.0.0 to 10.255.255.255. Class Bs are 172.16 to 172.31. And class Cs are 192.168.0.0, 192.168.255.255. There's a set of reserved IP addresses for loopback addresses, and that is the entire 127 range. So you typically won't see a 127 on the internet, and that's also considered localhost. So 127.0.0.1 is typically your localhost. And then you have what's called link local class Bs, which is when you have a DHCP when a device is looking for a DHCP address and it doesn't see a DHCP server, instead of just give itself a random IP address, it will give itself what's called a class B link local address, which is a 169.254/16. So that means that anything that gives itself a 192.1.254/16, it's going to make sure that nothing else has the same IP address as it, and then it's going to give itself, and then all of the things that are looking for a DHCP that didn't find a DHCP server are going to all get their own IP address so they can all talk to each other back and forth. I have a couple questions that I think pertain specifically to this section before we move on. So are there any downsides or disadvantages to supernetting? Hold on. To supernetting in a class C network as long as it is in a controlled environment? I assume that that means like going beyond like a /24 to a sorry, I gotta get my rest of myself up here. So going from like a /24 to like a /23. There's nothing particularly wrong with it. I am under the opinion that you should segment your broadcast domain, which is your network, make it as small as you possibly can, because as long as things can route to each other, that segments a lot of the need to just make this really large VLAN, right? So the larger your VLAN, the larger, the less safe that it is in terms of networking, because the larger the broadcast domain. So if there are any broadcast storms that happen, it's much harder to control. It's much harder to find where those problems are coming from. The more that you segment things and the more that you VLAN things off and make gateways, and as opposed to just a very large network, the safer kind of the whole network is in general, the more manageable it is from a networking engineer's perspective. Can you address public versus private IP addresses? Okay, cool. Yeah, I think yes, it was. I think I saw a typo where I used like a 19, like I used an incorrect subnet mask. Basically, on one of the previous slides, I think that there was, instead of saying, yeah, so this is a 126.168, and it should, or sorry, this is a 128.168, and it should have been something different, basically, that was within the class B addresses. But yeah, private versus public IP addresses. Yeah, so I use the word broadcast storm, and I do need to address what that is. So there's a couple different things that can happen during a broadcast storm. A broadcast storm could be completely accidental, and it could be basically a loop in the network. And when a loop in the network happens, the way that the switch treats broadcast traffic is that it takes it in over the port that it received it as, and it forwards it out over every other port. So what will happen is it will output over the loop, it will come back in over the loop, and then it will have to output it back over the loop again over and over and over. But then you get it back over the loop from the other side, and it has to continue the process. So you basically compound your switch with so much traffic, and so much duplicating the packet that it weighs the switch down, and the switch will actually stop forwarding packets correctly. This can be used as a tool by hackers to basically, similar to like what's called a DDoS attack, or denial of service attack, where you basically remove the ability for the user to continue working, or the entire network to continue working. This is why typically when we're building out networks, what we will do is we'll actually preach just standard IT safety fundamentals, which is like turning off ports, in like allowing security features that already exist on the switch to stay enabled, because oftentimes we get into scenarios where we will try to remove all the safety features because we're the only ones in the switch, so why does it matter? But it really only takes that one bit of access that someone that's malicious gets to the switch to just completely bring down an entire show. The best way to be safe about your network is to practice like IT safety fundamentals, which again is like as simple as turning ports off is one of the biggest things that you can do. Anything that's unused, turn it off. It takes like 30 seconds to log into the switch and turn a port back on. So I know it is an inconvenience, but it really makes for a safer network. Okay, so we've talked about specifically reserved IP addresses. So let's talk about layer 3 addressing from a switch perspective and kind of how that works. So we briefly talked about what's called an ARP message, an ARP request, briefly when we were talking about MAC addresses, and I didn't want to use that word because ARP messaging and the ARP system is something that the switch uses to send and receive packets and figure out what IP address is associated with what MAC address. And that's what ARP is. ARP is basically just a feature that the switch uses to say, hey, who is this IP address? Please tell this person so that they know. And then it keeps a record of all of the ARP tables. When the ARP table is literally just a table of IP address, MAC address, and port, MAC address and interface on the switch. So in this example right here, we're going to assume that L2 wants to send a message to 192.168.2.60, but it doesn't know the MAC address of that unit. We know that that's L6, but L2 does not know the MAC address of L6. It knows the IP address, but not the MAC address. L2 needs to know that info to be able to send that message, and to learn that message, L2, before it sends its packet out, is actually going to send an ARP request. And as we can see, that ARP request goes up to the switch. And then what the switch does, very similar to the MAC address, is the ARP request is then broadcast over the network. And like we talked about previously, a broadcast is sent over, and we'll talk a little bit more about it. Broadcast is sent over every single port except the port that it was received on. So L2 doesn't get that packet, just L1, 3, 5, L1, 3, 4, 5, 6, and 7. The packet literally says, hello, who is 192.168.60.2? Please tell this IP address. And so all of the other devices discard that packet because they don't need it. L6 says, that's my packet, I do need that packet. And then answers back what its MAC address is, and it sends basically a packet, an ARP response back to L2, back to the switch, saying, hey, this is my MAC address, this is my IP address, and now L2 knows the MAC address for that switch. And this is also something, again, like I said, this is done on a switch level as well, because the switch actually has typically an ARP table. And now that the sender knows the MAC address of the receiver, he can send the data, and the receiver confirms that he got the data. So now, before even sending the data that L2 wanted to send to L6, L2 actually sends an ARP request and figures out what information it needs to send to the data first, and then it sends that packet out. Okay, so I use a lot of terminology: unicast, multicast, and broadcast. We talked about multicast and broadcast. We didn't necessarily specifically mention unicast, but let's talk about those things, right? So unicast is, exactly like it sounds, one cast. So it is a packet that is sent from a single sender to a single receiver. No one else on the network gets it. If more than one receiver need the packet, it's on the sender to send two of that packet, one to one to one person and then one to the other person, right? So if I have, let's say L1 is sending a packet, L2 and 3 need that packet, L1 has to send a separate packet to L2 and to L3. In broadcast, it is a packet that's sent from a single sender to all the senders, and it doesn't cost that sender anything. They just say, here's my packet, send it out to everybody, and the switch says okay and forwards it out to every single host that's online at that time, except again, like I said, for the port that the host is on. The receivers get the packet even if they don't want it. They actually have to discard the packet if they don't want it, which is, takes up processing on the host. And then we have multicast, which is a lot more efficient than those specific like message types, not always applicable to every sort of application, but it is significantly more efficient. So we have one sender sending out a message to the network, and then it's the onus of all of the hosts that want that packet to say, hey, I want that packet, please give that packet to me. Which means that it requires each of those hosts to know, hey, I need that, give it to me, and then it tells the network to do that, and the network forwards it to that host, right? So you only have the processing speed of the sender isn't hurt by sending it to multiple people. It actually just takes the network a little bit more work to send it out to all those people, but typically not nearly as much as duplicating the packet on the host side and sending it twice. So talked a good bit about layer 3 addressing, layer 3 packet types, and now what we are going to talk about is the layer 3 IPv4 header. And we're just going to look at it just really quickly to just see if there's some things that you recognize. So some things that I can point out really off the top of my head is, so we have priority and type of service. So that equates to what we call QoS, or quality of service. We have our time to live, we have our version, and we have our source and destination IP address. So our source and destination IP address, obviously, those are things that we very easily recognize. Our version is our 4-bit, so that's our IPv4, IP version 4. And we have our QoS, and then we have time to live. We'll talk about all those things kind of as we move on, but like I said, type of service, TOS, QoS, they're all very similar terminology that all encapsulate what's called quality of service. Time to live, source to destination IP address. So when we're talking about quality of service, let's go a little bit deeper into that. So with quality of service, QoS, we probably all heard at least that terminology before. Hey, QoS. What happens is packets with a higher priority are routed before other packets are, or forwarded before other packets are. And if a packet with higher priority arrives after normal packets are already being routed, the packet actually jumps the queue. And so there's a good amount of terminology that we're throwing out here that could be new. So there's a couple of things here. So QoS markings. So QoS markings are a bunch of different things. There's basically something called QoS, there's something called TOS, and there's something called COS. So that all of those things are, COS and TOS are basically a scale of 0 to 8 typically. And what they do is it's just a queuing service. So it's like, if I'm a host and I'm sending out a packet and I say, this is a really important packet, I'm going to mark it with COS 6. And I know that to the switch, that means that it's going to queue it in a really high queue. There's also what's called DSCP packets. And if you've dealt with Dante and Dante switch configuration, you know that 56 is their PTP. That's the tag, the DSCP tag that all their PTP packets get, all their timing packets get. And 46, which is the DSCP tag that all of the media packets get. AS67 is slightly different. AS67, 46 is the PTP and 34 is the media. But regardless, basically, it's just a tagging system. That's all that it is. It's just an arbitrary number that is assigned to each packet as it's sent out to tell the switch, hey, this is how important this packet is. Now, something that I see a lot when we're doing switch configurations is that people will confuse COS and TOS with a queue status. So the queue is just a list of basically 7 numbers, and if your packet goes to Q7 or 4, it just depends on the switch model and the make and model. So say I have a switch with 7 queues, and I send my packet to Q7. That's the most important packet for the switch, depending on the switch model. And that's going to send out over at the highest priority at the fastest amount, right? And then if I send it over Q6, second to best. But it's very easy because it's a tier of 7 numbers, and COS is a tier of 7 numbers. It's very easy to think, oh, COS is the queue. And so what I'll see a lot is people taking a DSCP tag and associating it directly with COS and TOS type of service, as opposed to DSCP to queue. Now, in the SG300, which we're actually going to dive into at the end of this presentation, we're just going to look at the UI and stuff like that. It actually has the ability to take DSCP directly to the queue, and that's kind of what we're looking for here, because it's not necessarily helpful to say DSCP goes to COS, COS goes to queue, and that just tends to happen a lot. And I just thought I would bring it up because I do see it a lot. The thing that we need to look for when we're looking at network configuration is DSCP tags being associated directly to queues that the switch is forwarding those packets on. So if we look at this, these are all on what would be considered a per hop behavior, which means that each switch has its own COS settings, its own DSCP tag settings that each of them is doing. So every switch has to be configured individually. Once it hits the switch A, it's going to be forwarded over switch A and go to the highest priority queue, and then it's going to go out, and then maybe that switch at the other end of that network doesn't have quality of service configured on it, and so it really kind of ruins the why you had quality of service in the first place, because you have switches that do and switches that don't. It really needs to be uniform across the network in order to maintain a systematic forwarding behavior to lower the jitter. So you can choose which packet will be forwarded first. That's kind of what the DSCP to queue tags are. Again, like I said, the higher the queue, typically the smaller the jitter and the shorter the delay, because everything is now very specifically and methodically forwarded in a very predictable way. That's kind of what we're looking for here. We're looking for predictable behaviors. And then packets are handled typically according to DSCP. It just depends on the switch make and model. It depends on how you configured it. Typically, specifically small business switches like the SG300 will come with what's called trust DSCP, which means that it's just going to, based off of the DSCP tag, go to a predefined queue, and it's going to go, and everything's going to kind of be fine depending on what your application is. Another layer 3 protocol, like I said, QoS being a layer 3 protocol, another layer 3 protocol that we're going to see a lot of, that we've probably all already seen a good amount of, is IGMP. So IGMP, specifically version 2, because it's a little bit easier to kind of start there, and then we can, later on in a different conversation, start talking about the version 3. But there's 2 major parts to IGMP. IGMP has both a snooper and a querier. So in a network, you need 2 things. You need the IGMP querier, which is actually going to query all of the hosts and all of the IGMP groups, the multicast groups, and it's going to keep them logged. And then the snooper is what actually, IGMP snooping is what actually restricts the flow of multicast to hosts that don't need it. So often you'll see like filter unknown multicast, that's snooping at work right there. That's where it basically stops all the multicast that it doesn't know about, that that host doesn't ask for, and keeps it from it. So IGMP, packets are delivered only to the devices that are asking for them, which means that a host has to be like, hey, IGMP, I want this multicast group, and then that multicast group is forwarded on to that host. This avoids the packets that are delivered to all devices. So again, like I said, that's filtering unknown multicast that isn't necessarily needed to be forwarded to everything. That's where IGMP shines, because it keeps everything nice and neat. And without the flood control, things stop talking or things over talk, and then you get a bunch of packets that you have to discard, and it really bogs down all the processing power of all of the hosts that are on that network. Speaking specifically of networks, we need to address the idea of gateways. So the difference between what is called a layer 2 network and layer 3 network. So typically, if you have a layer 3 topology, you'll have 2 different networks. So if I have 2 different VLANs that I need to communicate between, and one of them has a bunch of hosts that are, on a /24, so we know that's a 255.255.255. I have 192.168.2.10 on one side, and then on the other side, I've got 192.168.42.60. So when I'm in this network topology, I can see that when I'm sending to a device that has an IP address in the same network, those devices know where to send it because it just sends it up to the switch forwards it to the correct port. We're good to go. So in this example, I want to take a packet from 2.10 to 2.30. It knows how to do that. That all happens within the switch and then this layer 2 profile, and we're good to go. Now, if I want to send a packet from 2.10 to 42.50, I'm actually not going to send it to 42.50. I'm going to send it first to the gateway, which is in between these two guys, which to this computer is 192.168.2.1. Now, you can configure what IP address the gateway is, but in this scenario, it's just the one. That's the easiest way to do it. That's kind of a best practice that you see a lot on the networking side. So let's dive a little bit deeper into that. So I've got my 2 networks, right? I've got 192.168.42, and I've got .0/24. So that means that anything 192.168.42, anything after that, we're good. Anything before that, we can't really talk to it. Same thing on the other side, 192.168.8.0/24, anything with .8, good. Anything with .9 or .7 or anything else, we're probably not going to be good. And so, like I said, we're going to assume that both of these networks are /24s and that they have a subnet mask of 255.255.255. Like, I know that this is redundant, but it's really good to solidify a lot of this information. So what we're going to actually have to do is connect those 2 networks together. And so we connect the gateway of the router of the 42 and the router of the .8 together. And you would think, okay, now we can just send packets to and from each other. Well, unfortunately, it doesn't work quite that simple. So we notice again, like I said, we've got 42s on one side, 42, 42, 42, and we've got 8s on the other side, 8 and 8 and 8. Which means, like I was saying, we have 2 networks. We've got our network 1 and we've got our network 2. And in order to send information from network 1 to network 2, what we actually have to do, like I said, is send it to 192.168.42.1 first. That forwards it off to the next router in line, and then that router forwards it off to the host. So I do want to take a second to talk about what a packet kind of looks like during this time, because it is important to understand. So when I send a packet from this host 192.168.42.100, and I want to send it to 192.168.8.80, the way that the packet looks is that it has the source IP address and the destination IP address, right? So we've talked about this. So the source IP address is 192.168.42.100, and the destination IP address is 192.168.8.80. That doesn't actually ever change. That is consistent throughout the life of the packet as it moves forward. What does change is the source and destination MAC address. So the source MAC address is actually the MAC address of this host right here, and the destination MAC address is the MAC address of this router right here. So while it's not the IP address, it's the MAC address. So that gets the packet from here to here. So what happens once it gets to that router? So once it gets to the router, what changes, again, is not the IP address, the source and destination IP address, but it's actually the source and destination MAC address. So the source MAC address now becomes the MAC address of this router right here. And the destination MAC address becomes the MAC address of this router right here. Same thing, forwards it off, gets it here, and then the same exact thing happens again. Source MAC address is this, source or destination MAC address is this host. But the entire time, 192.168.40.42.100 and 192.168.8.80 remain the source and destination IP address. It's important to know this because when you're breaking down packets and we're trying to troubleshoot, no matter where a packet is in the network, you're always going to see the correct source destination IP address and the correct destination IP address. Okay. So we've talked a lot about layers. And I just want to, now that we've kind of really fallen through a lot of these layers, I think that we should talk pretty briefly about what kind of happens when you go to google.com, right? So, and when I do something as simple as google.com, now that we understand what happens at each layer, now we can talk about like, you know, the practicality of all of that. So application layer is as simple as me going to a web browser and typing www.google.com. Okay, so I do that. The next thing that happens is the presentation layer takes over and it translates it from the application from what's called HTTP, and it translates it to network, to packets. And then the session is started. So that creates all these greetings for basically talking to google.com. So it says, hey, we're going to start a session with you, google.com. That's what happens in that packet. The next thing down the line is that we're sliced and diced, and we basically make, it's a TCP packet. So we create all the TCP headers. We say, this is how the packet's going to be all sliced up, and this is what it's going to look like. Then we bring it down to the next level, which is the network level, and we add our source and destination IP address to that packet, right? Then we add our source and destination MAC address to the packet. Then bits and bytes, it's sent out over the network via electrical impulses, and it's gone. Then we receive a reply back from google.com, and what happens? So first off, we get the notification on our, you know, on the network interface card. We've got bits and bytes coming back in. Those are packets. All right, we're going to check the source and destination data link, the MAC address. All right, that's good. We're good there. All right, we're going to check the source and destination IP address. Good to go. That's there. Then we're going to reassemble the message based off of how the packets are sliced up. So it's a TCP packet. So we're going to say, hey, got it. We got this packet. We want the next one. We got this packet. We want the next one. We see that this packet's actually not the right amount of bytes. So we need you to send this packet again. All that kind of stuff happens right there. Then the session layer. So this is the reply to that session layer handle information on the other side when we sent it, and it says, hey, here's your session information. We now have a session that goes back and forth. We're going to say we're session 5000. So session 5000 is what we're going to see in all of these packets that go back and forth just to get to google.com. Then presentation layer translates it into what is usable in the browser. And then voila, Google, we open and we have google.com. And all this happens obviously at the blink of an eye. You know, we type in google.com and all of a sudden Google comes up. So that is layers. Next, we're going to start talking about industry standards and 2110, but I just wanted to stop and pause for a second to see if there was any questions that we could chat through, because I'm sure that maybe we want to take a little question break before we move on to 2110 stuff. But if not, and I don't see anything, it looks like we're going to be good. So I will start.
This is Pete. I had a question. Could you explain again about gateway, what a gateway does? Because often in networks, you don't even bother filling in the gateway number, particularly if you're located in one location.
Right. So here, let me, just for a visual representation, because I'm a visual person, we'll go back to our, Okay, so when I need to, so like, you know, we had talked about it briefly, but when I need to send a packet from, so, okay, say I have two VLANs, right? So I've got an admin VLAN, and I actually have this at home. I have an admin VLAN and I have a user VLAN. So if but I need to get between the two VLANs. I need certain information to get between the two VLANs because say I'm walking around my house and I'm on my user VLAN because that's what the Wi-Fi is. But I need to control something on the admin network. I still want to be able to, so say my, my main source of administration is at 10.1.1.1. And I'm a user and I'm at 10.2.1.5, right? So if I need to talk between 10.1.1.1 and 10.2.1.5, I have to, between those two addresses, I have to put a gateway. So the message doesn't actually go just straight from 10.2.1.5 to 10.1.1.1. It actually has to go to 10.2.1.1, which is my gateway first, and then that gateway forwards my packet into the correct subnet. So this is, you can see this all the time when we talk about administration networks and media networks. You want to be able to get to the media port on like a Dante interface, but you want to be in the admin network. And so that's kind of where that comes in. Now, how do we get two VLANs to talk between each other? How do we get two networks to talk between each other? Well, we have to hit a gateway, because a gateway is literally the person that's taking your message, pulling it out of your hand, walking through the door and handing it to the other person, as opposed to you running out the door and handing it to the other person, because you're not allowed to do that.
So the gateway has to be the same on both of these VLANs.
Not necessarily. Right? So the gateway just has to be able to talk to each other. So for instance, like this, so say instead of this being two switches, for instance, this is just one switch with two VLANs on. So the minute I make a gateway of 192.168.8.1 and a gateway in this VLAN for 192.168.42.1, they are entered into the routing table of the switch. And so the switch goes, okay, the 8 network I've got over these ports, so that if I ever need to forward something to the 8 network, I forward it that way. And the 42 network is over these ports. So if I ever get anything that needs to be forwarded to 42, I send it over these ports. So as a 42, if I'm 42.100, I send something first to 42.1, and then 42.1 sends it to, technically 42.1 sends it to 8.1, and then 8.1 forwards it to 8.80.
Okay, that's good. You've got a couple more questions now from real outside people.
That's okay. All good. All right, hold on. All right, so got it. Okay, cool. That was basically, yeah, router to router or switch to switch. Most switches nowadays, just so we understand. So I talk about a router and a switch. So a switch does what's called switching, which literally just takes a packet, a layer 2 packet, and forwards it over the correct interface. It's very not necessarily intelligent. Now that's gross oversimplification. A router routes a packet from one network to another network. However, most switches nowadays are what are called layer 3 switches. Layer 3 switches are switches that also can route. So you'll notice, like, if you've ever messed with the SG300 or the SG350, a lot of the SG series stuff, you can actually have it be in layer 3 mode, and you can actually give it gateways and give it routers so that you point towards the, you have multiple VLANs that can route in between each other. So you could use a switch as a router, and you can use a router as a switch. It just has to do with the functionality of the make and model. And again, we can kind of dive into that once we get through this and we go into some of the more 2110 troubleshooting stuff. We can talk a little bit more about, like, I use the SG300 because I personally bought an SG300 for home networking stuff, and it's just easy to relate to because everybody's used an SG300 because of Dante and all that kind of fun jazz. So that's that. Why would a host use a broadcast instead of a multicast? Which type is used for what kind of application? So it depends on, typically it depends on the protocol that is being used. So when I as a computer, I'm sending an ARP message by definition is a broadcast. And so I send out a message that says, hey, this is a broadcast message. And what a broadcast message actually ends up being is it's an IP address. And typically it's called 255.255.255.255, which isn't actually an IP address that you can assign to a host, which is why the switch knows 255.255.255.255. That's a broadcast address. We're going to broadcast it. And so it just depends on what is being used. So like specifically like ARP uses broadcast addresses. When things don't know the IP addresses to other things, they broadcast to everything saying, hey, what's your IP address? DHCP, the ability to assign DHCP to users uses broadcasting, because when I plug into the network, I say, hey, what should my IP address be? And then the DHCP server says, hey, this is what your IP address should be, stop talking, and gives me an IP address, and then I have an IP address and can coexist with everything. Multicast is, again, like I said, protocol specific. So like typically you don't just send a multicast address, right? So multicast specifically has to do with like the application that you're doing. So Dante uses multicast sometimes. A67 uses multicast sometimes. And the computer or the host or the, whatever device you've connected to the network knows, hey, I'm going to send this information over multicast to this IP address. And again, multicast is a range of IP addresses. So it's by that IP address that the switch knows, oh, I'm going to treat that as multicast. I'm going to treat that as broadcast. So when I send something that's a 224.0.0.55, the switch knows that's a multicast address. I'm going to log that, and I'm not going to send it to anybody unless they ask for it. And that's kind of how that works. Gateway versus router. Gateway and router are typically synonymous. A gateway, though, speaking purely by definition, a gateway is typically the IP address that you send information to, whereas a router is like a physical box that routes. But a gateway is so like if you're filling out like the IP address form in your Windows or Macintosh computer, so you like 192.168.42.55, right? And then your subnet mask is 255.255.255, and then your gateway is 192.168.42.1. Well, that's the IP address for the router. That's your default gateway. So that's kind of how they're related to each other. Will I be able to show you how to set up a gateway configuration on a switch with multiple VLANs? I can. We can definitely do that. The only problem with that is I could show you how to do it specifically on the two switches I have here that we're going to talk about, but just know that it is quite independent of the manufacturer. So like Arista, it's a certain way, and Cisco, it's a certain way. But it's very different on like an Aruba, and it's very different on the Cisco SG300s versus the Cisco Catalyst series. Like it just operates in a different way because different UIs and different ways to organize things. Can we get an example of a gateway when you get to the setup of it? Yes, we can do that. So gateway is configured within the switch and assigned to specific ports. It's actually not assigned to specific ports. Similar to a VLAN, or I mean, in the same way as a VLAN. So you're doing inter VLAN routing. I've got VLAN 100 and VLAN 200. VLAN 100's address for simplicity is 192.168.100.1. Or yeah, VLAN 200's address is 192.168.200.1. So those VLANs are assigned to those ports. Think of the gateway as an IP address that lives on the back of the switch. And what you do is you send a message to the back of the switch. The back of the switch then forwards it to the other network, and then it gets to where it needs to go. I think that's probably the easiest way to understand like layer 3 switches, because again, it kind of gets confusing because a router, when we're talking about like the Cisco 2000 series routers, they were all physical pieces of hardware. They had like 4 ports on them, and those 4 ports could just be routing ports, so that it had an IP address associated with it. It had an IP address associated with it that routed to the next IP address or routed to another interface. But with a layer 3, you have to send kind of to like the software level of the switch, and then it comes back to the hardware level of the switch. All right. Is gateway usually the IP which is used to log? Yes, it actually typically is. So the question is the gateway usually the IP which is used to log into the switch? Definitely. You can turn that off so that you're not doing that, basically removing, but typically because that IP address is an IP address of the switch, yes, you can access and touch the switch through that IP address. Now, again, like I said, you can all turn that off. But if I go to my switch, my like core switch that I have in my closet, what I actually do is I can log into it through any of the IP addresses. So I can go to any of the IP addresses and go like 10.1.1.1. Okay, logged into that, or 10.2.1.1 and log into it through that. So yeah. Typically, those IP addresses are what are called SVIs. They're virtual interfaces that are on the switch that are assigned to each of the VLANs so that you can route. They're kind of like virtual routing interfaces. But again, that we can specifically talk all day about that specific one, but it might be a better conversation for a 3-day course, kind of CCNA kind of thing. But again, we could definitely talk about gateways and kind of like how you would set up a gateway on the SG300, just so you have an idea of like how it works fundamentally. All right. We can always come back to more questions. Not worried about it, but and especially at the end. But let's talk a little bit about 2110, the history of 2110, and the history of like some of these standards organizations that are out there, because sometimes it can get a little bit overwhelming, right? So when we talk about industry standards, there's a bunch of them that are out there, right? So there's like SMPTE, there's AES, there's IEEE, right? So let's talk about IETF. So IETF developed layer 3 IP standards. They developed something called DetNet, which is very similar to AVB, but the limitation of AVB was that it was only layer 2 and not layer 3. So they created it in a layer 3 method. So that's something that that is being evaluated pretty consistently. So then IEEE, which we've heard about a lot today, which is the Ethernet standard. They make a bunch of layer 2 standards. Like I said, Ethernet, they made the Ethernet standard, and they made AVB. So that was where AVB came from. And again, like I said, layer 2 standard, and that was actually ended up being why a lot of people didn't want to use it, because there was no way there's no way for it to be very, very largely scalable. And then of course, AES makes tons and tons of standards, and has tons and tons of standards for audio transport and control. And of course, SMPTE has standards for AV transport and control. So with all of these standards organizations and these standards that came out, and in terms of like how to not enforce the standard, but in terms of making it easy for consumers to know what is good and what's not, and what works and what doesn't, what's interoperable and what's not. JTNM was created, and they were the Joint Task Force for Network Media, and they're made up of a couple large standards organizations, mainly the EBU is a really, really big one, the European Broadcaster Union. They make up about 73 broadcast facilities across Europe, and they're very forward-facing, very network-based. BSF, which is plays into the birth of 2110 in general, is also part of JTNM and handles a lot of the JTNM organizations and meetings and things like that. SMPTE is part of JTNM as well, and NMOS. AMWA NMOS is also part of JTNM. Now we'll get into what NMOS is and what AMWA does, but just so we understand, JTNM is this large organization of these standards bodies that basically test. Their whole goal is to test a bunch of things just to make sure that things work together, right? So it's like, does a Riedel AS67 card talk to a Imagine Communications video device that does audio? Yes or no. And then they have these tests that they use to know whether it's interoperable or not. And that's kind of what they do. So that way you can go onto JTNM's website and literally look up a list of devices that you know work together in terms of 2110 and in terms of NMOS. And then, of course, there's more user-oriented organizations. So there's AIMS that promote VSF TR 03 and 04. We'll come back and we'll kind of get a little bit more history on 03 and 04 in a second. There's the Media Network Alliance, which promotes AES 67. And there's AVNU that does RTP over AVB and the promoted AVB kind of networks and stuff like that. So these are more user-oriented ones. They have manufacturers in them, but a lot of the users, the people who purchase these systems, are in these organizational bodies that kind of push VSF, push SMPTE to make things more usable for all of us. So we've talked about standards bodies and open source kind of stuff. Like I said, yeah, standards. And so now let's just look briefly at the proprietary approach to this. So there's a lot of proprietary protocols out there. There's Sony IP Live, there's Evertz Aspen, there's NDI, there's Dante, Ravenna, Livewire, OCA. This is kind of the birth of network, the rebirth of network audio. This is where, you know, it got really popular. A lot of the things that were lacking in the standards bodies were made up for by these proprietary protocols, right? So like Dante has SAP connections. That's something that, you know, hadn't really been seen. They have a really good way to connect two things together. Ravenna does too, Livewire does as well. You know, and there's positives and negatives to each of these things, right? So, you know, Sony IP Live has more license model based, so sometimes that can be tough for people. Evertz Aspen is Evertz driven, but it's standards based off of the VSF 03 and 04. NDI is focused specifically on a specific market, web and PC applications, while it's not compatible specifically with some of the SMPTE protocols. We've got the proprietary audio protocols down at the bottom. But when we look at all of these things, we look at all of these protocols, we see two things in here. We see the IP protocol, the header, IP, UDP, RTP, and then we see the payload. So realistically, a lot of these are very similar in nature in terms of the programming backbone, right? So it's very like they all have common roots. So if we look at proprietary protocols like Livewire, right? This was created by Axia Audio. It was a division of the Telos Alliance in 2003. It initially was only for radio installations with a minimum latency of about 0.75 seconds. 48 kilohertz, 24-bit uncompressed audio. That's a keyword there, 24-bit uncompressed audio. UDP included control and data plane. It was layer 3, and it could withstand 50 bidirectional stereo channels at 100 megabit bandwidth, but it was 1 gigabit compatible, right? And it had configuration software. We have Dante. So Dante was created by Audinate in 2006. It was made specifically for like local studio systems and events. It's a layer 3 based, minimum latency of about 150 microseconds, anywhere between that and 6 milliseconds. It can be at a variable amount of bit rates and at a variable kilohertz. So we can go 44.1 to 192, we do 16 bits, 24 bits, 32 bits. It's UDP, it has discovery, and it has a connection method. That's what that SAP is that I was talking about. So SAP basically is the method of which Dante uses to discover all of the connections that are available and then create those connections. And we'll talk about how we compare that to, you know, other connection methods as we kind of move on. But that's kind of like what SAP is. So SAP is this way that Dante uses to connect them. So when you click the dot and it turns green, that's actually SAP at work making that connection. You can use unicast or multicast. It uses PTPv1, 512 bidirectional channels and a link, 1 gig network. You know, it seems oddly similar to some of the Livewire stuff. And then we start looking into Ravenna. It was created by ALC Networks in 2012, sorry, 10. Layer 3, typical latency of 6 milliseconds, based on RTP, similar to everybody else. Unicast and multicast. It uses what's called SDP and ART RTSP for interoperability, and we'll talk a lot more about that as we kind of move on. We'll get a little bit more in depth on that. It uses PTP-v2, and it has a discovery using what's called zeroconf. Zeroconf is very synonymous with like Apple AirPlay, Apple Bonjour. So if you have Apple AirPlay or Google Chrome at home and you cast things and you discover like, oh, I have a speaker on Spotify in my home and I'm going to cast it to that, that's what that uses. It's called zeroconf, it's called MDNS, it's called Bonjour. They're not completely synonymous, but they're almost all the same thing. They actually use the same multicast IP address to transfer data around. And there's some really good things about that, but there's also some pretty frustrating things about that as well. And we'll talk about that as we move on. It uses web UI for configuration. It uses UDP, very similar to everything else, and it can be supported on corporate networks. So if we look at this, we log everything into a table, and we look at this, we see a lot of very significant commonalities. And the biggest commonality here that we see is that the format is what's called PCM. PCM is a format for uncompressed audio over IP. It's not necessarily specific to the audio industry. It's not necessarily specific to the broadcast industry. It's just a method to transfer audio over IP. So all of these actually use the same audio payload. So which means that technically, if you were able to decode everything else, you'd be able to get the same audio that you get from Ravenna to Dante, minus the fact that, the frequency is different and the bit rate might be different and the clocking mechanism is different. So the biggest problem between all of these guys in terms of the interoperability is the fact that they're all proprietary and they all have their own communication method, but they're all really similar. But basically, we see a world where there was a world that AES saw where everybody's saying hello in their own language, but they're all saying almost the same exact thing, right? So that is where AES 67 came along. Now, AES 67 isn't technically, I wouldn't actually consider it like a standard or a I would consider it a standard. I wouldn't necessarily consider it a protocol as much as I would consider it to be a least common denominator of all of these units, which is why there is still some, you do see some interoperability issues, and that's because it basically was made to encompass the least common denominator between all of these things. So if we look at that, and if we look at the open protocol and what AES 67 looks like, it was created by AES in 2013, specifically for broadcast radio and broadcast video. It's a layer 3 protocol. It uses already existing standards and builds upon them. And has a typical latency of 6 milliseconds, 48 kilohertz to 16 or 24 bit rate audio. Seems really familiar. It can use what's called SIP as a connection method. Now, SIP is, if you've ever dealt with VoIP, you have probably heard of SIP before. SIP is a method of connecting clients. Specifically, like I said, used in VoIP in order to connect a client and then transfer audio back and forth between the two clients. So AES 67 can use SIP as a connection protocol for unicast connection. That's actually how it creates its unicast connections. It says, hey, here's a hello message. This is me. Talk to me. Send me information back and forth. And they send me information back and forth. That's actually session level information. That's that layer 5 step right there. So it uses PTP-v2. It can be unicast or multicast. It includes control and data, and it can be used in corporate networks on a 1 gig network. So if we look, that looks strangely similar to all this stuff, except for the fact that it doesn't have discovery, because it used the least common denominator of all of these things in order to facilitate something that would be as interoperable as possible. The only thing that it doesn't have that everything else has is a proprietary method of connection. And that's just where kind of we'll start talking about SDP files. But this is a lot of information. I just wanted to pause because I figured before we start to go into the video side of things, I just wanted to see if anybody had any specific questions about audio. The only question I had thus far was, what is a SAP connection? And we will talk a little bit more about it, but I think I addressed it. If I haven't, let me know. Okay, cool. All right, let's move on then. Okay, so let's talk about video over IP. So SDI works great. SDI is an incredibly flexible and versatile way to pass video. It's something that we've used for quite a long time, but we're trying to move into the IP world. And as we were trying to move into the IP world, we thought we were real smart, and we were like, oh, well, what if we just take SDI and packetize it? And what do you know? That's exactly what we did, and that is what ST 2022-6 is. So when you hear 2022, when you hear 2022-6, really what 2022-6 is literally the whole SDI package packetized into a payload. That's all that it is. And so with that comes pros and cons, right? The pro is sync is easy because you just pass it on to the next thing. It's just packetizing it and sending it on. In-stream signaling is there. The issue that we run into is that there's unused bits, so it's a gigantic file, right? So it's that if you have 3 gigs on the SDI, you have 3 gigs on the network, and there's nothing you can really do about it. You can't split that up. And there's also the complexity of audio and video multiplexing. That means you still have to have audio video multiplexing on either side. So this is why 2022-6 is not nearly as versatile as we needed it to be in the AV world and the broadcast world in order to kind of move on and be fundamental and have something that actually truly replaces SDI in a way that makes it easy to use a networked system. Now, 2022-6 is absolutely still being considered and used in WAN transport because of some of the things that we're going to talk about next. Just want to see this question. So specifically regarding AS67 and AS67 switches, there's a question basically asking, there's not really such a thing as like what would be considered an AS67 switch, right? Because an AS67 switch is like, it's kind of a misnomer. What we really mean to say is it's a switch that can support AS67 traffic throughout. So he was pointing out that the Riedel manuals actually say, oh, if you haven't, like, they depict an AS67 switch. So when we say AS67 switch, what we're actually doing is saying a switch that supports these features that we would consider it good to use for AS67. So it's a switch that basically has PTP transparent boundary clock, which we will get very deep into in just a bit. It's a switch that supports QoS. It's a switch that supports IGMP snooping and IGMP querier. It's a switch that basically support native gig interfaces going through the network. So you're right, there isn't such a thing as like an AS67 switch, and to brand something as an AS67 switch really just doesn't work because a switch is a switch is a switch. Like the reason that there's so many standards that are involved with networking is because all these switches need to be able to do the same thing. And a lot of the switches that we're using do a lot more than just what we're using them for. But we know that if it has these features, specifically the PTP clocking features, we're probably going to be good enough. And that's what we would call an AS67 switch. It's the same thing. So we would never say there's a SMPTE 2110 switch. We would, however, say it's a SMPTE 2110 network, which means that there's SMPTE 2110 on it and can be fascinated through it. And then someone is asking if Milan is considered part of the AS67 spec. I'm actually not very familiar with what that is, but I can look it up and get back to you if I have your email address. We'll figure it out together. Don't worry. Okay, so really quickly back to video. So we just talked about 2022-6 and the fact that it's not quite versatile enough for what we need when we're talking about larger broadcast installations because it's just the overhead's too large. We're talking about way too much information. We have to have a bunch of equipment on the ends to de-encode a lot of that stuff, embed and de-embed. So then we came out with TR03. This is VSF came out with a spec called TR03. And what a TR03 stream looked like is actually, instead of one specific thing, they decided to split everything up into video, audio, and ancillary data. This was how this whole thing started. So they had an RFC 4175 for video, and that ended up becoming 2110-2. They had AS67 that they just repurposed for audio, and that ended up becoming and being modified into 2110-3 or -30. And then they had their ancillary data, which they drafted a paper for, and that ended up becoming 2110-40. So the reason that they split it up is because now a 2110 payload, a 2110-20 payload, which is video, becomes significantly smaller. So now when we're talking about a 3 gig video, now we're not talking about a 3 gig video, we're talking about something a lot closer to like a 2.4 gig video, where all the AS67 and all of the ancillary data are transferred separately. And that allows us for a lot less overhead. The other thing that really allows us to do is to separate all of the audio and video up. So now we have all of our audio that we can pull off the network at any given time. So any AS67 stuff that's going through the network, because it came off of a mic, off of the camera, we can pull that off anywhere in the network. Now it's not just all right, so it comes from the camera and it gets to the router, and then from the router we de-embed, and then that goes into the console, and that's how we get that information. It's like, no, well, we don't have to do that anymore. Now everything is connected to the internet, not the internet, the 2110 router, sorry, the 2110 network, and we just pull all of that kind of stuff off of the network, and we don't need to do a lot of the de-embedding and embedding anymore, because it's all right there in the network. So there's a lot of pros and there's some cons to this, right? So it's all elemental flow separate, and it's very, very efficient. Now the con is that it is timing sensitive, right? So we can't, after TR03 was published, SMPTE came out and said, okay, we're going to take this and we're going to expand upon it, and we're going to come up with 2110. And so 2110 was formed into sections. So 2110-10 is our system timing and definitions. That's our PTP, right? So that is PTP v2 right there. That's 2110-10. When people say -10, that's what they're talking about, PTP v2. -20 is our uncompressed active video. -21 is what's called traffic shaping and delivery timing for uncompressed active video. So this was something that was very important to define up front, and it basically had to do with how traffic got from one part of the network to the other. So it is a part of 2110 spec to basically show how you're deploying your network and get traffic from A to B in a manner that works for 2110. So in here is actually instructions for how your senders and receivers need to be able to get audio and video off of the network. We have our 2110-30, which is our PCM digital audio. Oddly enough, it's almost exactly the same spec as AS67, except it's a lot more fine-tuned. So there's a lot more to it. There's things that have to be there that don't have to be there in an AS67 world. Basically, it just makes it a little bit easier for manufacturers to interact with each other. 2110-31. It's a little bit different than 30. It's actually AES3, but packetized over the network. It's not just completely packetized, but basically what it does is it allows us to reuse the AES3 user bits and passes across the network. We were actually doing this when we first developed our AS67 solutions for panels. Originally, we were sending user bits over an external method, and then wouldn't you know it, Dolby uses AES3 for all of their Atmos stuff. And they said, we need a way to transfer AES3 across the network. And so that is when they pushed for it real hard, 2110-31 was created. And this is basically a way to send user bits and AES3 audio across the network. Then we have our 2110-40, which is our ancillary data. So the ancillary data is 2110-40. That's where you'll see a lot of closed captioning, time code, a lot of that kind of stuff will be there. So that's all well and good, but we run into a little bit of a problem as we expand. And the problem is that nobody wants 1080p anymore. That's not true, but we're moving towards 4K, right? And what is 4K? 4K is 12 gig audio. But guess what? Basically, with this 4K video, if we're trying to send this over a 10 gig link, it just doesn't work. That's not how audio works. And now it's not actually 12 gig. It's what it actually is like, it's like 10.5, which makes it even worse because it's like, we just need that little bit more. So within that was created this spec within the SMPTE 2110 world called SMPTE 2110-22. And what that spec is a 1:4 compression ratio that, which is technically, it's called visually lossless compression. It compresses the video and the metadata down and sends it out basically in a 3 gig package over the network. So that means that 4K can be transported over a valid, the 4K that can be transported over a valid SDI signal can now be put in 2022-6 and compressed and sent out over a JPEG XS. Now, when you do this, obviously, we don't like to hear the word compression. Compression means complexity, compression means latency, and compression means loss. You know, we're getting losslessness of some kind. Now that, you know, you could say visually lossless all you want. There's such a thing as mechanically lossless, but that's really tough to deal with. Now, as we move to a 25 gig world, this is going to be much less of a problem, and we're just going to send 4K signals over this whole system anyways. But for now, JPEG XS, specifically 2110-22, is very, very, very usable for basically deliverables. So I can now send over a 3 gig network a link to my, my service provider. I can send my 4K signal out to them over JPEG XS as opposed to having to send it on a 25 gig signal. Makes it really nice for compression and stuff like that. Okay, so that's most of the 2110 stuff specific to 2110 that I'm going to cover. We're going to come out of 2110 for a second and talk about the things that surround 2110. So that's 2022-7, and that's NMOS. So let's talk about specifically redundancy features. I actually see a question up in the chat about redundancy feature right now for 2110. So 2110 is a redundancy feature for that can be it was actually developed for 2022-6, but it is and can be used for 2110 spec, whether it's 2110-30 or 2110-20, whatever it is. So basically, the way that it starts out is that I have a camera and I have a monitor, right? And I've got a switch in between, and so I've got my information going from one side to the other side, and that's fine. That's fine and good, excuse me. But there's not a lot of redundancy there, right? So what if I added another switch and I allowed it to send a duplicate packet over what we would call a blue network? And what we actually say is A and B, or amber and blue, or red and blue, amber and blue because A and B. Now, something that is often misleading is that this looks very similar to other redundancy features, like say maybe a network A and a network B. Typically what we see is people say, oh, well, it's like that doesn't always work. If A goes down, then, it takes a second for B to come back up. Well, the way that 2022-7 actually works is it sends redundant packets, the exact same packet at the exact same time over each of the network interfaces. And then they go across the network and they arrive ideally at the exact same time at the other interfaces. And those interfaces can actually decide on a packet by packet basis which one they would like to use, the red one or the blue one, the amber one or the blue one, A or B. Which means that if you unplug A at any time, B is always going to be there to take over. If I plug A right back in, unplug B, A will always be there to take back over. It doesn't matter which one is which. It will always look at both packets, say, hey, that one's actually corrupted. I'm going to use this one this time. Hey, that one's corrupted this time. I'm going to use that one. So this is a very, very robust, very good way of creating a redundant system that's a little bit different than other other redundancy features that we've seen kind of in IP audio and IP video thus far. And that's why this is why the term seamless protection switching comes from. It's that it is actually seamless, so it doesn't matter. And that's actually part of the NMOS. Sorry, the AMWA. No, it's part of the JT&M testing. They actually they have a feature where it drops packets from each side at an inversely proportional rate. So it's like it'll just keep flapping back and forth, and your device basically has to stay on the entire time. And that's kind of where that comes from and why 2022-7 specifically is so important. All right. So control. Control is a big topic. Control's a really, really big topic right now. How do you control a 2110 network? Well, the first method that we have is called SDP, Session Description Protocol. So Session Description Protocol is basically a method of, it looks very similar, and it is basically a text file that outlines all of the control data that you need for a signal. So if I have a signal coming from an AES67 card to another AES67 card, or a Lavo router or any other AES67 device, what I can do with 2110-30 is take an SDP file. I can just export an SDP file, and I can import it to the other device. And this is kind of what an SDP file looks like. So you'll notice in here that we have pretty much all the information we would ever need, starting with the source IP address. So this is where this IP address is coming from. That's where this stream is coming from. It tells me the stream name. It tells me the IP address of the stream, so the multicast IP address of that stream. It tells me the port and what kind of audio it is. So it's RTP, and it's RTP payload style 96, which is kind of just important as we kind of move forward. We'll kind of talk about that. It's not super specifically important to 2110 in general, other than the fact that you know what your payload type is. So it's like typically it's just 96 by default or 97. And if it's wrong, then you won't get the image on the other side or the audio on the other side, but if it's right, you will. So it's just important to know more than anything, but it's not really important to dive into the granularity of it. We can see that it's 8 channels, payload type's 96, like we were saying before. Excuse me, sorry. We have a 24-bit packet, and at 4800 kilohertz, 48 kilohertz. And we have our clock information right here. This is really important. This is our PTP clock information. This is what tells us, hey, here's my stream. By the way, this is the master that I'm clocked to. So if that's incorrect, we're not going to see it, and it'll actually throw an error that says, hey, the clocks aren't matching. This is not going to work correctly. So if we look at an example of a 2110 SDP file, very, very similar, right? Same sort of information, just a little bit more. So we've got we've got YCBCR information in here, our height and width. We've got all the same information that we had before: payload type, payload port, multicast IP address for the source, the name of that. So all of the things that we need are embedded in this SDP file. Now, if we look at specifically the artist interface, just because I've got it right here. So, and I look at this, all that information is right here: the payload type, the receive buffer, the packet time, the bit depth, the multicast port, and the multicast IP address. All of that information is right there. And all we actually have to do is click this import SDP file, and it actually imports all that information for us. And it's the same thing if we were to do an AES67 output. We could put in all that information and then send out an AES67 an SDP file for our next thing down the line. Now, that can be kind of annoying. I mean, like, really annoying, right? You don't want to import and export SDP files for every single source and destination on your network. That's kind of crazy. So NMOS came around. AMWA and NMOS came around. So it's kind of like 2110's search engine a little bit. So there's 3 main components that we're going to talk about today. There's a lot more to it, but I don't think that those things are, we'll talk about a couple other things, but for the most part, there's stuff that's not specifically necessary to like what we're talking about today, which is like controlling a 2110 network. So 3 main components, right? So we've got ISO 4, And you guys, some of you probably heard of these specific terminologies before, and some of you probably haven't. But we have ISO 4, which is our discovery and registration. So that's how we actually discover devices on our network and register them and know what they have. We have ISO 5, which is our connection management. So that's kind of a keyword from what we were talking about when we talked about all those proprietary methods. They had connection management. So Dante uses SAP for their connection management. Ravenna uses SIP and RTP and SDP files. And ISO 5 is what 2110 is going to, or 2110 is using in order for connection management. That's what AMWA is doing with that. And then we have ISO 6, which is our network control. So when we talk about ISO 4, we can kind of think about it like a pizza menu being listed on DoorDash. So if we go on DoorDash and we say, hey, that's a registered restaurant, and I want to go in and look at that pizza menu. Well, that pizza menu is registered on DoorDash. So we go into DoorDash and we order the pizza that we want. And that's kind of what that connection management is. Now, we can order the pizza all we want, but sometimes it doesn't take the best path to get back to us, right? So like if we just call the pizza place, like, hey, send me pizza, here's my address. Sometimes you can't track it. You don't know the way that it's going. Sometimes it takes longer than you would want it to, and you can't keep tabs on it. That's where the network control comes in. That's where the ISO 6 comes in. That's kind of like DoorDash saying, hey, make sure to take this route when you're giving this pizza to this person, right? That's kind of how that works. Now, if we're going to dive a little bit more into the workflow, right? So what this kind of looks like is we start off with a couple components that are going to be connected to our network. We have a receiver device, we have a sender device, and we have what's called our ISO 4 registry, our NMOS registry. That's kind of where you'll hear NMOS registry a good significant amount. The NMOS registry sends some NDNS information out to the server that says, the network that says, hey, I'm a registration server, please register with me. The sender sends MDNS to the network, the receiver sends MDNS to the network, and then all that comes back up here and it's registered right here. And so what happens is each of these, the sender and receiver uses this great API that's used a ton in programming and networking called the RESTful API. And there's a lot of what's called HTTP posts, HTTP gets. And in fact, what we're doing here is we're using that RESTful API to HTTP post the resources from the sender and the receiver to the NMOS registry. And once it does that, we can actually go into an NMOS browser and see our NMOS device. So we have right here, we've got a Grass Valley camera, and a Grass Valley camera is giving us these two connections that we could make to that camera, right? So that's what we would look at when we looked at something that was talking to our registration server. Now with ISO 5, the workflow is a little bit different. This is how the communication is actually established between all of the devices, right? So this is our control system. This is our registration server right up here, right? Or sorry, this is the control system. This is the registration server right down here, right? So what happens is, once we decide what we need, so this is us making a connection, right? So we say, hey, I want to connect camera to monitor. So when we say that to this control system, to our NMOS Explorer, it sends an HTTP GET to the sender. And the sender sends back its SDP file. And it sends it back up to the control system. And then it sends an HTTP post to the receiver. And when it sends an HTTP post to the receiver of that SDP file, now the receiver has the SDP file. And so what it does is it actually joins, it does an IGMP join for that multicast group to the network. And now that connection is established between sender and receiver. So all that ISO 5 is a slightly more, like, it's complex on the back end, but it's very simple on the front end. It's a more universal and quick way to transfer SDP files from sender and receiver. You're just not the one that's doing that. You're not going into the sender and going, all right, export SDP file, go into the receiver, all right, upload SDP file. That's how ISO 5 works. Very simple, very versatile, very scalable. Now, before I move on to the next slide, I do want to mention ISO 6. ISO 6 is a way to manage the network as a whole. Now, typically, and by that I mean like ISO 6, like if you had an ISO 6 device that was controlling a network, what you would actually see is that the device is saying, hey, I need this, you're going to send a flow this way through this path and send a flow this way through this path. That's what that's doing. Now, the tough thing about that is that that's something that's already been sort of developed by companies in a very proprietary way, and those are called SDNs. SDNs are basically what happen when you take the control plane off of the switches and you move it to an external device. So now instead of having to go into each switch and being like, show IP IGMP snooping, show IP IGMP snooping, show IP IGMP snooping to every switch, I just have one central location, one central server that manages all of my switches that I say, show IP IGMP snooping this switch, enter. And then I say, I want to do that on all the switches. So I click, do it on all the switches, I get the reports from all of those switches. So this allows me to do a whole lot and to manage which way I'm sending all of my IP address, all of my multicast, and how that is reaching, it's going from A to B in terms of like queuing and all that kind of good stuff. Again, like I said, ISO 6 is not really being developed nearly as much as it should be, but that's because there's a lot of other really good applications on the market already that are being developed. Cisco actually has one of their own. That's specifically built for broadcasters to manage 2110 traffic going through the network. And what that ends up looking like on a larger scale is we have our broadcast controller up here, and it's telling our network controller, that would be like our ISO 6 device or our SDN, I need this, this is what you need to give me. And it manages how the network is treating all that multicast information. And it's getting it from source to destination without a lot of overhead on any of the devices, because now the network is managing a lot of that pushing and shoving around. But the goal here, realistically, is to have a registered network with all of our devices and our controllers and our flows, and we don't have to deal with, I want this thing to go to this thing. It's like, no, it's just a broadcast controller, and now I can do everything. And this is where that interoperability comes in. Now, because instead of having to like have separate protocols that everything speaks, that we have to go to VSM and say, hey, VSM, we need you to speak all these protocols. We just have one big old protocol that talks all of these things. And that allows us to make this very large cohesive system. And this is where we are today. We are kind of moving in that direction. ISO 4 and 5 are very widely adopted. ISO 6, like I said, is not so much, because in those large installations, a lot of those broadcasters have chosen to go with proprietary methods. And so that's kind of where we're seeing that go. So, like it's something that is to be watched pretty closely, but it's definitely something that like we're seeing very, very, very close on the horizon. We're already deploying very large 2110 systems with NMOS and using it in a way that competes with an SDI router and an SDI workflow. So the other thing that I wanted to talk about, this is ISO 7. But basically, this is just really quick. So we talked about ISO 6, now I want to talk about ISO 7. It's basically just a way to transport tally across the network. So when it's so that we can get things from A to B without having to go through GPI cables, without having to go through tally systems. It just transfers tally directly to those things. And that is most of it for NMOS stuff. We will go very deep next into IGMP, or not IGMP, sorry, PTP, and talk a little bit more about that. Are there any questions? I see questions specifically about IGMP and talking a little bit more about that. We can do that, and we can talk a little bit more. It's actually a lot easier to show. So when we start to go into the switch, we can kind of push a little bit that way. All right. All right. Okay. So let's start talking about PTP. I'm sure most of us who have dealt with any sort of networked audio, whether it be Dante or AS67, have dealt with PTP before and or the pains of PTP. So first of all, what is PTP, right? So we talked about PTP, we talked about that it's 2110-10, but realistically what it does is it replaces a sync pulse generator. It was started in 2002. IEEE spec for it was IEEE 1588 2002 or PTP version 1, and that is what Dante uses. So Dante uses that IEEE 1588-2002 PTP v1. And it was created to specifically synchronize financial transactions. There's tons and tons of rules in Wall Street on banks and what kind of sync generators, PTP sync generators they need. But it also is used for mobile phone tower transmissions and basically anything that's timing critical, right? So then 2008 rolls around, they release a new PTP version. It's PTP version 2-2008. It improves accuracy and precision robustness, but it is not compatible with 2008. It's not compatible with 2002. Not backwards compatible. Okay, so let's dive into a little bit of what this is and how this works, right? So starting off, very simply, we have a master and a slave, okay? So our master and our slave are free running. So they're gonna free run at 12:00 and 11:59:40, okay? So, and they're gonna chug along, and they're gonna notice that each other, 12:00:01 and 11:59:41, those are not in sync. So what's gonna happen is, my master is gonna send what's called a sync message, and it's gonna take a timestamp. There's gonna be a lot of timestamps. So it's gonna take this timestamp, and this timestamp, you'll notice, is the timestamp that it sent the sync message, right? Okay, so, and then our slave is gonna take a timestamp, 11:59:43. But you'll notice that there is something wrong with this picture, right? So it takes time for the sync message to arrive at the slave, and that is a problem. And that's something that's going to be addressed later on, and we'll talk about that and how this all works, right? Okay, so sync message goes, then guess what happens next? A follow-up message is sent, and this time there's information in the follow-up message. The follow-up message is sent with the information that says, hey, this is when I sent my sync message, just so you know. Great. Slave's got a timestamp that, 12:00:01, and we're gonna take the difference, and the difference is about 18 seconds. Great. Okay, so what our time was gonna be right here was 11:59:45. So we're gonna add that to 11:59:45, and we hit 12:00:03. Awesome. That's what our new time is. We're gonna adjust our time to that. We did. And we're gonna keep running along. But guess what? 12:05 and 12:03 are not the same time, oddly enough. Scary how that works. So we're gonna take a timestamp on the slave side, and we're gonna send what's called a delay request. When we send our delay request, when we send our delay request, it's going to arrive at the master at 12:00:09. And when 12:00:09, when it hits it at 12:00:09, the master is going to send the timestamp and send a delay response back to the slave, and the slave is going to say, "Oh, you got that at 12:00:09. Okay, I'm going to take that timestamp, and I'm going to take the difference. So the difference is about 4 seconds, right? And I'm going to divide that by 2 because the packet went one way and then went the other way. We're going to divide that by 2, and that gives us 2 seconds. And so when we have that 2 seconds, we're going to take what our time was down here, which is 12:00:11. It was going to be that, and we're going to make it 12:00:13. And that is how PTP v2 specifically works. I do want to address, I see in the questions saying PTP v1 is compatible with PTP v2 existing on the same network. v1 users see v1, v2 users see v2, v2 users can also send out v1 for the v1 users to see. So that is mostly correct. v1 and v2 can absolutely coexist on the same network. v2, the protocol for v2 is not backwards compatible for v1, which meaning that if I send out v2 messages, a PTP v1 device can't use those messages. So if we look at, like IGMP, and again, we'll talk a little bit more about IGMP as we go. IGMP v2 and v3 are completely backwards compatible with each other. So a v3 message is automatically pushed around. But if you have a bunch of v1 devices and a bunch of v2 devices, the PTP will not talk to each other. And I do mean to say that they can coexist on the same network. It's not impossible for them to coexist, but the protocols are independently not, they're not backwards compatible, meaning that V2 messages aren't going to go to a V1 and the V1's not going to be like, oh yeah, I recognize that and I'm going to sync to that. So that is what I meant by saying that V1 and V2 are not compatible with each other. I didn't mean to say that they can't coexist on the same network. But so like a Dante device, when it's in the Dante mode, not AES67 mode, it can't use any PTP-v2 packets. Once you turn it into PTP-v2, when you turn it into PTP-v2 or AES67 mode, then it starts to use AES67. PTP 2059. So I see a question that says which PTP version is used in SMPTE 2059. So SMPTE 2059 and SMPTE 2059-2 are PTP v2. If you've heard about PTP v2, sometimes you hear about what's called message rates and media profiles or profiles in general. SMPTE 2059-2 is a profile of PTP v2. And all that means is that it's a specific message rate that's associated with PTP v2, right? So PTP v2, the IEEE 1588 standard says that there will be, I'm probably gonna get this wrong, but just for example's sake, says maybe that there will be 1 announce every second, and there will be 2 sync messages every second, and then there will be a certain amount of delay request and delay response messages. The 2059-2 profile says that there will be 1 announce every second, or sorry, yes, 1 announce every second, 8 sync messages a second, and 8 delay responses every second. So that's kind of how SMPTE 2059-2 uses PTP v2. So I hope that clears up some stuff. And again, we'll talk more about PTP profiles as we kind of move on and we go into like touching base with the actual like the boundary clock switch and all that kind of stuff. But just talking about general PTP across the network right this second, the way that this works when you send PTP across the network on a non-compliant, non-1588 compliant switch, and what I mean by that is not that it won't pass PTP, because most switches will, almost any switch will pass PTP, but what I mean by that is it doesn't have any PTP boundary or transparent clock. And like we were saying before, PTP v2 and PTP v1 can absolutely coexist on the same switch. It's not gonna like screw everything up. But what a simple switch does is it doesn't have any PTP compliant features. So it decreases the quality and the reliability of PTP going across the network, right? So that basically means that all the jitter that's being used for all the jitter that the switch is creating, even though it may just be microseconds or nanoseconds of jitter, really mess those packets up when there's nothing to basically compensate the packets for that. So the number of possible switch hops is drastically reduced with this, since the network traffic will increase and therefore the scalability and the flexibility of the network is significantly reduced. And then when we say a COT switch, we mean a commercial off-the-shelf switch. So, so this is not a recommended scenario. This is why typically we don't specifically advise anybody to go out and buy like an SG300 for use with Bolero, because it's really hard to guarantee the accuracy of all this without something that's PTP aware. So when we talk about a non-PTP aware switch, there's some pitfalls that end up happening, right? So we have our PTP grandmaster and we have a slave right here. And so what we're going to do is in blue, we're going to send our sync messages through our non-PTP aware switch. And then we're going to send a delay response message back. And we're going to send a delay send a delay request to the PTP grandmaster and a delay response back to the slave. And then we're going to add another slave, right? So this is all well and good, and then we do the same thing, except that when you do this, because PTP is all in the same multicast group, everybody gets everything, right? So now we actually double up our delay requests and our delay responses. So what happens if we add a third device? Well, it's the same thing, but now we triple all of our stuff. So you can see how very quickly, especially in a scalable model, this can become a little bit cumbersome for the switch and for the devices to kind of narrow down what they need. It can kind of lead to some issues, right? So we have increased traffic and have repeated delay requests and delay response messages. We have increased delay with each switch hop because limited network size with non-P2P or switches. We have no control over the P2P offset. So there's no ability to kind of move things around. We have increased jitter because each switch is not compensating for its own jitter. So we have, as a result, we have decreased reliability of slave devices. So let's talk about when we're talking about P2P aware switches, let's talk about what that means. So the first of which typically you see is called a boundary clock. This is kind of like where this is the creme de la creme kind of stuff. So then we talk about a boundary clock switch. So let's say we have a master and a slave and a switch, a boundary clock switch in the middle. So we're going to send our PTP to the switch. And what happens is right here, that becomes a slave port. So this port and this device actually have a master and slave relationship to them that is disparate of the rest of the network, right? And then what happens is using that information, not the packet, but the information, the boundary clock syncs with the master. So we have a master-slave relationship here, and then the packet actually doesn't leave this interface. It stays right there, and then the switch uses that information to continue moving on. So then what it does is it makes this port and every other port on the switch a master port, and it sends PTP out of that. And so very similar to how this is a master-slave relationship, this is also a master-slave relationship. So this is not necessarily clocking directly to the master, but it is clocking to the switch, which is clocking to the master. And this allows you to clock a relatively, not an infinite number of things, but a significantly larger amount of devices on your network, because you're not having to deal with how much stress you're putting on the master. You don't have to deal with how much jitter is on each switch, because they're compensating for that because the switches themselves are synchronized. And so now these two guys are in sync. So let's just recap what that looks like at a different scale, right? So now we have our PTP Grandmaster, our PTP aware boundary clock switch, and slave 1, 2, and 3. So we got our PTP master and our PTP slave. So like I said, this is a master and slave relationship right here. And they send their packets back and forth between each other. And then we have our PTP master and PTP slave right here. They send their packets back and forth to each other. And it's the same thing as we go through the network. This terminates the PTP session, if you will. I don't think that's the correct terminology, but that's what that does, is it actually terminates this. So a packet from this device isn't actually forwarded up to the master. It just ends here. Just the PTP packets ends here, and then the switch is in control of what's in sync and what's not. So via PTP aware boundary switch. So boundary clock switch terminates the PTP connection from the master and creates a new PTP connection towards the slave and client. Boundary clock removes the packet delay variations of the PDV between itself and the next upstream clock, right? So that means that the jitter that it creates by processing the packet, even though however small it is, it can completely compensate for that, because we're talking about timing. It's just timing information at the start, timing information at the end. And boundary clocks may be installed in every network element for the highest level of performance at the slave client, which means that every switch, ideally you have everything on your network being a boundary clock. That's like the ideal scenario. This allows for significantly larger networks. I wouldn't say like infinite networks, but I mean significantly larger networks. So let's look at a transparent clock. That's the other type of switch, right, that we're talking about. So with a transparent clock, it's a little bit different. We're still relying on the master to send a bunch of packets to the slave sending a bunch of packets to the master. But let's send PTP into it and see what happens. So the switch takes a timestamp at A, and they're at 12:0004. Cool, we got 12:0004. And then the switch processes that packet to send over, and it realizes I spent 2 seconds. This is not a real world example, but it makes, it's just an example. So I spent 2 seconds processing this switch. Great, awesome. So what it's going to do is take another timestamp at B, and then it's going to take the PTP plus the timestamp B plus the processing time, and it's going to forward all that information off to the slave. When the slave gets it, it does a calculation. It realizes that it needs to be 1204 and not 1206, and you have an in-sync scenario. So transparent clocks, like really solid, use typically a little bit cheaper than boundary clocks, but it takes into consider the processing time incurred within the switch. The transparent clock modifies the PTP packet as it flows. So it is still the same packet that flows from A to B technically, but they're adding information into it to say, hey, I messed with this packet for you. It removes only its own processing time. It doesn't remove any other switch's processing time. So you can't put a transparent clock in there, but you can put like you can't put a transparent clock in there and it just fix everything, but you can put a transparent clock in and it'll fix its own information, right? So it does not terminate the PTP connection like we were talking about with the boundary clock enabled switch, and it is not completely scalable to a limitless size. And the reason that this is because, at some level, a master whatever is going to run out of ability to sync slaves because it's got to respond to every single delay response of a single delay request. So this is good for small, medium-sized networks, and by small, medium-sized networks, I mean it's like, larger, not like 5 Bolero antennas and a couple belt packs or something, but like a significant size, but maybe not a corporate size network. So that's those two switch types. That's a boundary clock and a transparent clock switch. So I see a couple questions. I think this would be a good time to answer these. So besides the maximum number of recommended slaves before boundary clock is needed, what other signs would indicate the need for a boundary clock? So a lot of it's very modular, right? So it has to do with the size of your network in terms of host size, in terms of network size, and it also has to do with the like you said, the amount of slaves. So ideally, when you're dealing with a lot of switch hops, you want at the very least to have a boundary clock at the core and maybe a transparent clock at the edges. But just remember that typically a boundary clock will have a limitation of what it can clock. So, you have like a master clock that can clock, 500 items. After 500, it really starts to bog down and it's really hard for it to continue working. So you add a boundary clock in to really remove that. But if your boundary clock, if each port on your boundary clock is supporting 100 slaves off of a non-PTP aware switch, that taxes the boundary clock. And that's something that the boundary clock often can't really do. It's not supposed to do that. The most ideal scenario for a lot of these systems is to have PTP boundary clock or PTP transparent clock from end to end, which can be tough, but it ends up being like the most feasible way to make sure that the entire network is clocked. And again, it really has to do with the amount of slaves. That's like one of the biggest things is like the amount of slaves and the size of your network. If we're talking about, like a couple switches and not a ton of traffic, you could probably get away with like a boundary clock to transparent clock. It's not that big of a deal, right? But if you're talking about a big corporate network, almost everything has got to be boundary clocked because it just you're going to run into issues so quickly, and it would be so much better if everything was just boundary clocked, and so all of your end devices clocked to the boundary clocks up, and nothing specifically being taxed a whole lot. I see a question that says, does IEEE 1588 require a boundary clock, or is it either boundary clock or transparent? So IEEE 1588 doesn't specifically state none of the RFCs, the requests for comments, or the IEEE specs talk about having to have a boundary clock or a transparent clock. And a lot of times we'll actually talk to financial guys and they'll be like, you don't need a boundary clock, it's not that big of a deal, because they're talking about hundreds of microseconds or even tens of microseconds. And we're talking about one. That's the stipulation that we're talking about here. So IEEE doesn't specifically call for boundary clock or transparent clock, but the IEEE or the PTP synonymous, the you can use a boundary clock or a transparent clock. It will both be compliant with the IEEE topology, right? So if you had like a boundary clock and a transparent clock, the IEEE is not going to come knocking at your door saying you did it wrong. And again, these are all built within the IEEE specification. So boundary clock and transparent clock are part of the IEEE specification for what you could do, not necessarily what you have to do. How does it work with multiple transparent clock switches? Does each switch add a timestamp? Each switch does add a timestamp, and each switch, it's not like an additional timestamp, it just adds to the value. So if we were to go in and view, which we can do that. We can, well, actually, well, we can, but it would take a little bit of time. I won't do that today. But if you go into like PTP TrackHound or another tool that can monitor that information, you can actually see the timestamp that it adds. And so it'll just add to that value every time the packet goes through a transparent clock switch. And now, honestly, what you'll end up seeing with transparent clock switches is very, very low nanosecond offsets. I mean, we're talking about like 10, you know. But the issue that you run into with transparent clock is the ability to, you're still putting all the onus on a single master device as opposed to spreading out the need to clock everything. Is there topology for a redundant clock system? Yes, there is, and technically, there's a whole lot of things you can do, and I don't want to, you know, go too deep down the rabbit hole, but you can very easily. So, like, one of the things that we've, you know, had discussions about in terms of WAN transportation, you don't typically. PTP was never made to transport over like ISPs and stuff like that. It was never made for that. It's facility specific typically. But you can transport AES-67 pretty well if you have, say, a GPS locked PTP Grandmaster on one side, PTP clocked Grandmaster on the other side. So what we're actually about to talk about is the best master clock algorithm, which is kind of how like a redundant clock would work. It doesn't always work seamlessly, which is why I don't usually pitch it as like, oh yeah, it's completely redundant, but it is like a way to have multiple master devices able to like pick up the slack when something else doesn't. Another question says, imagine you have 7 Lumen X wired into a star, the 22 AES-67 artist panels, 48 Boleros, and 20 Bolero antennas, 6 AES-67 artist cars actually reduce the Bolero antennas. Oh wait, I'm missing some of this, and that's my fault. I don't fully understand, and oh, got it. Nope, don't got it. Okay, so I think what the question is like, if you have
a question a little bit before that was the beginning of that question.
Oh.
Besides the maximum number of recommended slaves before a BC is needed, what other signs would indicate the need for a BC?
Oh, in terms of that, so it says, let's say 7 Lumen X are wired under a star, like, would you maybe need a boundary clock at that point? I mean, I would say yes, because at this point you have and I assume, I don't know about this specific topology, if this is a specific thing or not, but if this was a thing, I would highly recommend having a master clock, because it would be really, really tough to clock everything off of a single Bolero antenna. You could also do there's a couple things you could do. You could segment your PTP domains so that not everything is clocked off the same master. That kind of frees up some processing power. But yeah, I would highly recommend having a boundary clock somewhere in there to help. The issue again with the boundary clock is that you're putting a lot of weight on it depending on how many things are being synced off of that like boundary clock master port. But again, it sounds like this is a pretty specific scenario. So if you have questions, we can definitely sit down and talk through whatever this application is. Yeah, I would recommend doing a boundary clock, or at least some boundary clocks, maybe when you have like a ton of things. So like if you had like a core switch where most of your AES-67 cards were plugged in, some of your Bolero antennas were plugged in, and then everything else is a transparent clock, that would be very good. Else, you could do, and we'll talk about it a little bit later, what's called PTP hybrid mode, to kind of take the weight off of the network and the slave devices if you have a master clock. But the 7 Luminex is not going to treat you wrong. It just needs to be talked about what the master device is and how the slave device is reacting. Will PTP track count show you what type of clock is being used and where? Luminex doesn't say in their documentation unless that's the E2E to P2P part. So it is not E2E to P2P. E2E to P2P is very different, and we actually don't. P2P is used very rarely, especially in the SMPTE 2110 and media world. PTP track count will, well, PTP track count will tell you by proxy what you're doing, but it won't just be like you're using a end-to-end transparent clock or you're using a boundary clock. But we'll actually talk about what that looks like and how to differentiate that when we kind of come to the application level stuff. So we'll kind of talk a little bit through PTP track count. We'll talk a little bit through some troubleshooting steps, that kind of good stuff. So, okay, so let's talk about best master clock algorithm and some redundancy stuff. So with best master clock algorithm, there are, the best master clock algorithm is a way for PTP devices to decide who is going to be the master and who is going to be the slave. So in this scenario, the best master clock algorithm is listed as follows. First looks at the priority 1. We'll talk through all these. Clock class, accuracy, variance, priority 2, and then clock identity, which is based off of the MAC address. Priority 1 is usually firmware based, so it is usually not changeable. When it is, it's fine, but it's just important maybe not to change that because that was changed specifically by the hardware manufacturer, so that because it's the first thing that things look at. So I wouldn't want to go and be like, so for instance, I have an SPG 8000, right? So a Tektronix SPG 8000 outputting PTP onto the network. Its priority 1 by default is going to be like 124, depending on the PTP profile that I'm using. So what I do then is then not change that and change everything else, but I'm not going to change the PTP1 because that PTP1 priority is already lower than everything else. So it's kind of important not to really mess with the PTP1 because typically PTP1 is even, and when you make something higher, you're making it, it's the only way that it can be for the rest of time, basically. The next thing that the best master clock algorithm looks at, which is what all of these devices are participating in, is clock class, which is hardware defined, clock accuracy, which is also hardware defined, variance, which has to do with kind of network activity and what it sees between it and all the other devices. Then we look at priority 2. This is the priority that typically you can change. So typically we'll look at priority 2 as like, if you're in Bolero, if you know Bolero, that's what you're changing. When you're changing the priority, you're changing the priority 2 value. We don't allow people to change the priority 1 value because it's already set in a way to make master clocks and like master SPGs be better than it and not make other things be, be worse than it because we're trying to comply with IEEE, or not IEEE, sorry, SMPTE 2110 standards, which basically say that like, technically, in a full 2110 system, your master shouldn't be something that's sending and receiving audio, technically. And this is, ignored a lot, especially for smaller systems, which is fine. But for larger systems, it's very important that your master clock not be something that's actually sending and receiving audio or video. And then, of course, if everything's exactly the same all the way down to the bottom, we're looking at clock identity, which is based off of the MAC address. So if everything's exactly the same, you're basically going to be picked on based off of whoever has the lowest MAC address number, and that's all that there is to that. But what this allows us to do is if we lose a master clock and we have another master clock available, that master clock is going to take right over. Again, it's not always instantaneous, so I'm hesitant to be like, yeah, that's a perfect way to make your system completely redundant because it's not always a seamless changeover, but it is. It does add some level of redundancy. Maybe, you lose like a second or two of audio or drop or something like that, as opposed to, losing the whole network. But okay, so let's talk a little bit more about like the logistics of PTP, right? So if we talk about the PTP group, we talked about a bunch of the message types, right? So we have sync, follow-up, announce, which we didn't really talk about in management. We talked about delay request and delay response. An announce message is sent out by the by any PTP device that just plugged into the network to say, hey, I'm here, I could be a master. And then if it gets an announcement back that says, no, I have a higher priority or I have a better clock class, then it says, okay, you're gonna be the master and I'm gonna be the slave. And then it goes back into its corner and does whatever it wants to do. So that's what the announce message is. The management message isn't as integral to specifically like all AES-67 applications, but it is part of PTP protocol. But the PTP multicast IP address, where you will see all the PTP information for that network, is 224.0.1.129. That means if I were to go into Wireshark and look at a Wireshark trace and go host equals, or sorry, IP address equals 224.0.1.129, I would see all the PTP messages that were sent or received. So then let's talk about hybrid mode, because hybrid mode is really, really important for this. So when we're talking about, you know, that overload of messages that go to every single slave when we double up the network and it really gets dicey, what hybrid mode allows us to do is, instead of the delay requests and delay responses being sent via multicast, because they're specific to each user, those actually become unicast messages, and that significantly reduces the overhead for the switch, and it significantly reduces what each of those PTP clients have to do in order to figure out what their delay request and delay response messages are. So when you get to a really large system, you really want to be in hybrid mode. Especially if you're not if you're boundary clocked, it doesn't really matter all that much. But if you are transparent clocked or not clocked on the network side, it is extremely important to be hybrid mode. Otherwise, you will start to have issues with hosts basically not being, like, they'll fall out of time all of a sudden because they'll be like, oh, I was looking at something else. That was my bad, you know. So this is kind of what this is just very briefly what a network might look like. So you maybe have ordinary clock going to a transparent clock, something that doesn't have a lot of hosts on it. And then you have a bunch of hosts on this boundary clock switch, so you actually clock the boundary clock off of a transparent clock ordinary grandmaster right here. And you have all your slave devices clocking to the boundary clock on that, because maybe there's more on the boundary clock and less on a transparent clock. And so you think everything that can handle can handle all of that kind of basically, if you have a low enough count on a transparent clock switch, you're good. Then you can hang a boundary clock switch off of that, and that can do a majority of your processing power to handle all of the rest of your devices, right? And that is about it for that. But obviously, there's more that we're going to do with the SG300 and stuff like that. But I think this is a really good time to open it up to questions as I get some of this stuff prepared. All right, so what I'm going to do here really quickly, I'm going to pull up a couple things.
Are you going to address PTP settings for Bolero specifically?
Yeah, we can definitely do that. Let me, yeah, because we're going to do some troubleshooting with Bolero. So while we're doing that, we can
Cool.
We can talk about like what default is.
So like the card versus the antennas versus the master antenna, what's the ideal setting for them? Yeah.
Right. Yeah, we can definitely do that. Okay. All right. So I don't see any specific questions. So we can just start doing a couple like little troubleshooting steps. Okay, so before we go into this, we actually do need to do this because I broke the system on purpose so that we have to fix it. And then we can go into PTP track count. I saw a bunch of questions on PTP track count, and I just wanted to open PTP track count and talk through kind of some settings and kind of some information that we can talk through to help with troubleshooting. But so I'm here with a Bolero system. So I've actually got my Bolero system set up on Artist, so I don't need to do a whole ton of work there, and I'm not going to cover that because that's kind of a separate conversation in of itself. But I know that my antenna is 10.10.1.101, And I know that my cards are 71, 72, 73. But I'll notice that there's a couple things that are a little bit alarming here. I know for a fact that I can see all of them and I'm connected to the same network as them. I'm actually routed to them, which is even more indicative that I can see all of them on the same network. But I'm not seeing each of them in and of themselves. So what I can actually do, I could go into my switch and I could just start fiddling around and see what I could do to figure out what's kind of going on. And that's fine. But you know, I could end up after a long 8-hour day not figuring out what I need and being really stressed out. And all that I really had to do from the beginning is log in and do a mirror port and start looking at some of my my Wireshark traces and stuff like that. So that's actually what I'm going to do here right now. I'm going to go in here and really quickly, I'm going to look at my status just so that I can give you guys an overview of what my switch looks like over here. So right now I've got the switch. I just want to just to throw out some knowns that I know because I set the switch up. So I've got these two ports right here that have nothing to do with this assignment. And I have this port that also has nothing to do with this assignment. And then I have this guy, which is my uplink to my core, which is over in the closet over there. But these ports, port 5, port 6, port 7, port 8, and port 9 are all on a VLAN that is like the Riedel VLAN for right now. And so I've got all my Bolero and all my AS67 cards connected to it. And I'm just going to really quickly verify, just for everybody's sake. Got my 666 VLAN right here, and I've got just to show you guys port VLAN membership. Yep, I've got 666.666.666.666.666, and I've got my access, right? So those are all access level ports. They're all connected, but we're still not seeing something. So
were those just arbitrary names you gave that VLAN, and that's the VLAN name you put in there?
Yeah, I already had a bunch of VLAN tags, and so I just threw in 666 because I just thought it would be kind of funny.
But do you have to do something to make it a tag, or you just pick the number?
So if we're yeah, so you kind of want to get into like the configuration stuff. Is that kind of what I'm understanding? Like,
I just wondered where that number 666 came from.
Oh, I just popped it in because I was being stupid.
There we go.
No, it's completely arbitrary. I just made that VLAN because I had put a bunch of stuff on my switches already, and then I needed a Riedel VLAN to add on to that. So that is that. So what I want to do is I want to mirror the port of, say, my antenna. And I know for a fact, let's just take a look here. My antenna is connected to port 6. So I'm going to go to administration, diagnostics. And so this is the problem that I have necessarily with showing you guys this method is this is only one switch manufacturer, but you can do this on almost any switch manufacturer. I can go to somewhere in their diagnostic function is the ability to mirror a port. And so that's what I'm doing right now is I'm mirroring a port. I'm going to be plugged into GE4, and my antenna is plugged into GE9. And I'm going to say I want type TX and RX. I want the 2 in the front. Okay, got it. So you notice it says status not ready. The reason it says status not ready is because I am not plugged in, and I'm going to plug in right now. And now that's active. So GE4 is mirroring. GE4 is mirroring GE9. And so what I'm going to do, just so that this doesn't.
Stefan, Pete,
yeah.
We're losing you. Your voice is getting a little jittery. You want to just turn off your video there, see if that proves it?
Yeah.
Just turn your camera off.
Let me webcam. You guys got me?
We do.
Awesome. Okay, so as you can see here, what I've got is I've got GE4 mirroring the TX and RX of GE9. I see a question in the thing about in the chat about IP structured VLAN. We will cover that, but I want to do this Wireshark trace before we get before it kind of gets confusing. So I'm plugged into GE4, and I'm just going to tell you right now, my dongle is plugged into GE4 from this interface right here. And what I've done is I've actually given myself a static IP address in that VLAN so that I will get all those packets that I need to, and it won't discard a bunch of packets. Cool. So what I'm going to do now is I'm going to open Wireshark. This is a free downloadable application that you can get online, and it is, like I said, completely open source and free, and you can pull it up. And honestly, there's classes that can be taught on Wireshark. So if you're interested in Wireshark and its capabilities, I highly recommend doing like a Udemy course or something on it, because it is very extensive. So got that one Office native VLAN right here. So I'm going to double click that. All right. So I'm seeing, let's just go ahead and stop it for a second. I'm seeing a lot of information from 10.10.1.101. I'm not seeing a lot of other 10 dots between this guy. So if we just scroll through, and I noticed that, so say, let's look at PTP, for instance. So let's just start with PTP. So I'm going to do IP address. Oh, there it is. I've done this before. It's weird. And we're going to look at just PTP. And I'm going to notice that all of my PTP only comes from one place, and it's me. It's that Bolero antenna right there. So this is an obvious indication that there's something wrong on the network. Something is missing, right? So what I'm going to do here, because I'm looking for IGMP messages. So IGMP, we were talking about it earlier. IGMP is what actually allows us to send and receive multicast messages. And if IGMP isn't working correctly, or if we're not receiving any IGMP, that's a good indication that there's something wrong with the multicast forwarding, with how the switch is treating multicast. And so that's something that we can look into. So I'm just going to search IGMP. So when I do that, you'll notice that nothing comes up. Okay, so that's an obvious indication that something is wrong here. So just to recap, we're looking at PTP. We notice that only our device is sending PTP as far as we can see, and we're not seeing any IGMP messages. Okay, this gives us a really, really strong place to start looking in our switch, okay? So let's go back here. So there's a bunch of different options here. I can see there's a multicast option. So if I go to multicast, and I'm looking through these, I know that there's a couple things, and again, I don't specifically, we can talk about how to enable and disable IGMP snooping on each switch, but because this is a specific switch manufacturer and every switch manufacturer does it differently, it'd be best to actually just look some of this stuff up. So actually, I can go SG300 enable IGMP snooping. And it will literally come up with, honestly, like the first thing will come up with how to set all of this up, how to enable this. So I can see that I need bridge multicast filtering, and I could tell you this, but I just want to show you like how easily inaccessible all this information is. So I can see bridge multicast filtering status needs to be enabled. I can see I need to enable the IP IGMP snooping status, and I need to enable it per VLAN, right? And the IGMP snooping table, I need to also edit it and enable it per VLAN. Okay, so there's some things that we can definitely look for here, okay? So the number one thing, the first thing on there was bridge multicast filtering status. I know for a fact that bridge multicast filtering status, if not enabled, will completely break IGMP snooping on a Cisco SG300, just by personal knowledge, but it's good that we have it enabled. Okay, so now, let's go here to IGMP snooping. And we'll see that one of the things we're looking at here is that IGMP snooping status is actually set to disable. And if we look at each of these VLANs, the operational status of each of these VLANs is set to disable. The courier status is set to disable. So there's something wrong here. But let's enable IGMP snooping and see what happens. I'm going to go back to Wireshark. I'm going to start it over again. We're going to give it a second because it takes a second to kind of boot up and query all of those items. You'll notice that this is the query address.
Can
Sorry,
you zoom in a little bit more into Wireshark? It's very small type, if you can.
Yeah. Yes, definitely. I will do that. If you notice, the query IP address is still 255.255.255, which is just basically a null IP address. And when I refresh, it's my main router that's in my closet over there. So that's good. That's kind of what I wanted it to be set as. And now if we go back to Wireshark, here, I will zoom in here, and then I'm going to stop it. And I'm going to search PTP v2, or just PTP. And we can do that, or we can do the IP address like we did before. So before, you'll notice I did IP address and search the IP address of PTP, or I can just search PTP. And I'll notice now we're going to scroll all the way down to the bottom, and I'm getting a ton of other devices that are sending and receiving PTP all of a sudden. Okay, cool. So we've got that. We've got a lot of multicast going back and forth. And if we search for IGMP, oh my goodness, glory, we have a ton of beautiful IGMP, what are called reports and queries. So this is where we start to talk about reports and queries. So you'll notice here that we have two things. We have an IGMP snooper, or snooping, and IGMP query. We talked about this a little bit earlier in the presentation. So the snooping is what actually gatekeeps all of that multicast, right? And actually opens it up or closes it, opens it up and closes it, and all that kind of good stuff. So the querier is what logs all of that. So if I go to my multicast, if I go to my, let's look at this guy, IGMP snooping IP multicast group, it's going to show me all the multicast groups that are associated with this switch. So I've got 224.0.1.1.2.9, that's PTP right there. So I've got some other stuff that's specifically related to Bolero. If this is all in the user manual, but 230.4.4.1 is firmware. This has to do with audio. This has to do with configuration. This is audio. And this is also audio, lots of audio. Okay, so that's a lot of really good information right there. Now, I just want to point out the reason typically when you disable IGMP snooping, what happens is you just get a flood of IGMP messages, right? You just get tons and tons of messages that you don't want to have to deal with. But what I've actually done here, and this is actually a very good thing to do, is I've filtered any unregistered multicast. So what the querier's job is to do is to query the people who want the multicast, not necessarily the people who don't want the multicast. So if no one asks for the multicast, then the multicast is technically not registered, which means it will just be forwarded. So what I've actually done here is filtered any unregistered multicast, and now it won't send any unregistered multicast to things that don't want it. So this is just a good way to clean up your network and not deal with any sort of weird thing where like you're just getting a bunch of multicasts that you don't want. So that there's a ton of options here. Mainly the ones that you need are this one, IP IGMP snooping. You need this to monitor your IGMP, and then you need the unregistered multicast tab. Now you can find all that information. What I literally did was just SG300 enable IGMP snooping. And this is by now I know kind of the way that most CLIs do it, so I'll do most of this on the CLI. But if I didn't know that and I wanted to go and figure out how to enable IGMP snooping on like a Catalyst, I could say Catalyst 9300. Enable IGMP snooping. And when you know it, here is a catalog of every command associated with IGMP on the Catalyst 9300. And I think down here, it's going to show us a little bit more about how to configure it. So configuring the device as a member of a group. So it's enable, configure terminal. Actually, this is just how to like add a specific group, but enabling IGMP. Actually, technically, catalysts have it enabled by default, but enabling a courier is a little bit different. And so if I want to deal with that, I can go back here. And it's going to tell me all about how to enable a query. This might have been exactly the same page. But again, all the information is there online. If you need information, Cisco has tons and tons of resources. Arista has tons and tons of resources. Juniper does. HP does. Dell does. Lots and lots of resources devoted to this kind of thing. So that's kind of what. If I don't know something, I Google it, and then if I can't find it on Google, I go and call. I try to call someone up that may know it. But that's kind of how we kind of learn a lot of this stuff. That and CCNA. The CCNA course is really good. Okay, so we've got this. So I'm going to address a couple. There's a question specifically about like why you would want to separate VLANs and have separate IP structures. So when I'm setting a switch up and say I have traffic that I don't want to necessarily talk to each other unless they're really, really trying. So basically, if I want something to be like, I want this IP and talk to it, then I would separate it by a VLAN and route it, because that's something that's totally possible via router. That's not very possible by that you wouldn't normally do if you didn't know the exact IP address you're trying to talk to, right? So if I'm trying to reduce my traffic and reduce my broadcast domain, I can separate things out into VLANs. In fact, a lot of larger topologies, what they'll do is they will have every single port on a switch a routed port, and you'll have one IP address that routes to everything else in the network. So it actually segments everything down to the point where you only have one host and one router per every single port. And what that does is it very much segments that broadcast domain. And when I say that, segmenting the broadcast domain basically means to remove the ability for broadcast traffic to flow. So I can't broadcast across a router, but I can, and I can really screw a bunch of stuff up if I'm all in the same VLAN. So the tighter and smaller your VLANs are, the tighter and smaller your IP structures are, the more clean that traffic is kind of going to flow. It's more just best practices than it is anything else. And a lot of that has to do with like, I would highly recommend, if you're interested in this kind of stuff, actually, the question just came in. Would you recommend taking a Cisco Online CCNA course or something like GNS 3 videos or Udemy? Yes, absolutely. And a very, very good thing is right now, Cisco has finally gone away from only using the Pearson VUE in-class testing, and they are now testing people online in their homes, which means that all you have to do is go to YouTube, or not go to YouTube. I would highly recommend not going to YouTube specifically, but going to like Udemy for $11 and get a couple courses. I have a course that I use, and it's a Scottish guy with a really thick accent, but he has labs, and the labs are very, very helpful, and it really helps you understand a lot of this stuff in a more concrete way. Because again, a lot of this IP structure stuff, these are just common practices in the network world that we carry over into the broadcast world. And so that's why I would never discourage someone from taking a CCNA or an ACE or something like that. There's another question. Fast with Audinate and Dante networks, I have set an IGMP static group for the PTP multicast address to make sure clock data gets to every device no matter what. Is this not good practice with PTP-v2? Should I let IGMP snooping filter the clock traffic? You don't have to. You're not doing anything wrong. You're just doing it the hard way. But typically we do things the hard way when things aren't working correctly, and we know that the hard way works. So yes, realistically, technically for PTP-v2 and PTP-v1, you can absolutely let IGMP snooping do the work for you. Now, there are some issues that that arise. Mainly, you can only have one querier in a network, right? So when you have multiple queriers and they're not talking very nice to each other, sometimes you have issues with basically queriers trying to take over each other. And then you have a loss of all of those IGMP groups. There's a whole bunch of things that could go wrong with an IGMP snooping querier if you haven't set everything up very concretely. Typically, that only happens with cross-vendor switch platforms. So that happened specifically in a situation where we were using, and it's not even that cross-platform, we were using Nexus at the core and SG300s at the edge. I would not recommend this, by the way, but we were doing this, and the SG300s basically would continue to take over the querier from the thing. I will pull it up. Let me pull it up in another tab, and then I will pull it back in. Someone just asked for the class suggestion, and I'm just going to pop it in. Now, there's pros and cons to the guy that I'm about to show you, because he is a little bit harder to understand, slightly, because he's got a pretty thick Scottish accent. But again, the thing that I think is very important about what he has is labs. He has labs that you can just download and do with Packet Tracer and GNS3. Please don't play. Yes. Okay. All right. So this is the course that I took that is very, very good, and he updated it for the new CCNA course. So in February, they changed the CCNA course material from like 100-something to 200-301, and they changed some of the course material, and you'll notice that it is updated, and he has basically put up new stuff for the 200-301 exam. And just as a reminder, I can't stress this enough because this is kind of historical in terms of the networking world. Cisco, for the first time ever, is allowing you to do online testing for this. So if you ever wanted to get your CCNA and have that on your resume, now is probably a really good time to do that. I don't know if there's a place that I can post this link, but it's very simple: udemy/course/CCNA-complete. So, okay, all right. So moving on with this kind of troubleshooting scenario, let's look back at this. So when we're looking at this, now we have all of our stuff seeing each other, everything's super happy. And we've got tons and tons of data flowing back and forth that we can see. And what we're going to do now, I just want to show you guys, if you guys are having, there's just like how modular and how much you can do with this. Let's pull up PTP TrackHound, and let's run through some information, and that's really good. I was going to do some stuff where you can actually decode audio, but I think that's probably less important than walking through PTP TrackHound if PTP TrackHound is something that's necessary. So when I open PTP TrackHound, there's a bunch of stuff that's probably not all completely useful to everybody, but mainly up here I've got filters, and you notice I'm not actually getting any PTP information at all. So what I'm going to do is I'm going to hit Interface Office Native VLAN. That's my mirror port. And that allows me to listen and to subscribe to all of the PTP traffic that's happening on that port. And if you remember, we did TX on RX, so we're going to basically see everything that this guy sees up here, which is pretty much everything. So there's a bunch of really good information. There's a bunch of really good information specifically. So let's talk about the announce rate and the sync rate, right? So this is what we're talking about when we talked about those media profiles. And those media profiles are basically just a list of the announce rate, the sync rate, and then what the request rate back to the host is, right? So in this case, our announce rate is 1 announce message per second, 8 sync messages per second. And then it's kind of variable depending on what each of the hosts need, either 1 or 2 requests a second, or 1 to 4 sometimes. And so we'll see that kind of populate here. One thing to note is you should never see multiple grandmasters unless they are on a different domain. So if you start to see announce messages flying around from something else, something is going wrong in this in this PTP world here. So one of the questions earlier was asking about if PTP TrackHound will show us the transparent clock data, and it will. It's going to show us that here, and it will show us in the sync messages. So see how there's a timestamp here? See how that timestamp is 0? Well, hold on. Stop. All right. Not the timestamp, sorry. There, basically in here is a clock, correction. Here we go. Basically what we have here, so I see a question that's asking if we're talking about 2110 related issues or Bolero related issues, or if we're kind of on a network heavy tangent. So yes, we were kind of on a network heavy tangent with the CCNA course and stuff, but a lot of these things with PTP are all related to SMPTE 2110 related issues. They cross over very much into into Dante issues because they all use a similar mechanism, and PTP TrackHound can allow us to look into that. So the question in the past was where do you see if you're using a transparent clock or a boundary clock? And so if you want to see if you're using a transparent clock, what you need to do is go into here, any of these messages, and go to PTP, and there will be a field called correction. You notice that this correction field says 0.00 nanoseconds. That's because we're not using a transparent clock switch. If we were going through a Luminex, which I unfortunately don't have in my little office here, then we would actually see this correction value change peer by peer, packet by packet. Now, what we will see when we're doing a boundary clock is we will actually only see two things. And I actually have a boundary clock switch here that I would like to jump into. I don't know how much time we're going to have to do that, and I don't want to get too granular if we want to remain a little bit more surface level with some of this stuff. But basically what you'll see is under Grandmaster, you'll see the same IP. You won't see the IP address, but you see the same clock identity. And then below it, you'll see it'll say BC for boundary clock. And then that'll be it. That's all that you have. So if you're connected to anywhere in the switch, you're only going to see what the Grandmaster is and what your boundary clock is. And that's all that there is. So that's kind of how, if you're in PTP TrackHound, you would know if you're on a boundary clock switch or a transparent clock switch. The other thing you can do is look up the features for each of those switches online. So like if you do like a keyword search for, so like Arista 7280, IEEE 1588, you'll come up with stuff that talks about persistent time protocol for either the specific switch or maybe for in general for the manufacturer. So now I can look at the 7280 data sheet and I can search IEEE 1588, and would you look at it, Arista's hardware derived persistent. So then you have basically a system for that. So that's another way to know if your switch is PTP, whereas typically the data sheets will show it. So this is a very versatile tool, but there's technically nothing in here that's different than what you can do in Wireshark. This is actually just a modified version of Wireshark, but it's modified in a way that allows it to be very, very PTP specific, so that we can take a look at what the Grandmaster is, what the slaves are, and if the status of anything kind of changes, right? And what is interpreted on that level. And if things change in here, we know, okay, there's something that we need to look at. There's something we need to talk to a network engineer about. There's something that we need to go and say, hey, what's wrong with IGMP? What's wrong with, why are we losing a PTP packet every so often? Because that is a big issue. If we start to get audio dropouts, typically, a lot of times it will be PTP related. Okay, so what I'm gonna do We talked briefly about administering this switch. I will talk a little bit more about like what it kind of looks like to set this switch up more from scratch with some VLANs and stuff like that, where to look for all those things, how to add an interface. So if you notice, I have, if I go here and I see my VLAN 1, I have a VLAN 1 of 192.168.1.254. And then on my VLAN 100, I've got an IP address of 10.1.1.6. Now, if I go to IPv4 routes, and I look at that, I can see that I'm going to route to my 10.1.1.0 network in my VLAN 100. And if I need to do the 192.168.1.0 network, I can go to my VLAN 1. So this is, I just wanted to address some of the questions that were coming in about like how this works on a switch by switch level. So because of these interfaces, so if I was an interface in VLAN 1 and I wanted this switch to route me to another VLAN, say VLAN 1, I would say this is my gateway. So when I set up my gateway over here, I'm going to set up my gateway to say 10.1.1.6. And then every packet that I need to send to a different network is going to go to 10.1.1.6, and it's going to go across into this next network that I need. So that's kind of like, I just wanted to address that question from earlier.
Excuse me, do you have to set the reverse gateway as well?
Yes, so the gateway has to be set on both sides in order for bidirectional communication.
So the other one would be the 192.168.1.254.
Exactly. So it's got to be on both sides to do that bidirectional communication. So, all right. So that's kind of how this like virtual IP address for gateways work. Now, when I'm setting the switch up, kind of the first thing I end up doing, along with a couple other, little things, I turn off like green Ethernet because green Ethernet can really screw up AS67 devices in general. And then I go to VLANs. And so if I look at my VLAN settings, I see that I've made a bunch of VLANs. All that I have to do to make another VLAN is go to VLAN ID and say 800. VLAN name is VLAN 800. And I click apply. And now I've got this. Now you'll notice that it says VLAN interface state disabled. The reason that it says that is because it's not assigned to any ports that are active. And so by default, when Cisco does not see that a VLAN is being used by a port that's on, it will disable the VLAN interface. So now what I'm going to do is I'm going to go back to my IP configuration just so that I have another route in here. I'm going to add one. And I'm going to say,
it's going to be on our website as a video. Sorry about that. I didn't have my mic on.
Very good. And we're going to add another destination IP address. So I'm going to say 10 dot, let's say 10.8.1.1, 24. Oh, sorry, I was like, I say, this looks really weird. This is the wrong thing. This is routing. I need to add an IP interface first. Okay, so in VLAN 800, I'm going to add a static IP address, 10.8.1.1. Network mask is going to be 255.255.255.0. And if I don't want to do that, all I got to do is go down here and say 24 and click apply. So that's VLAN 800. VLAN 800 now is 10.8.1.1. Cool. So then I go down to IP4 routes, and it automatically, once the VLAN is up, it will automatically add a 10.8.1.0 and a directly connected link. So now that I've created my own VLAN, what I'm going to do is I'm going to assign it to some ports. So I'm going to specifically assign it to, let's say, port 9. 800, go. Port 9, untagged. Cool. So port 9 is now 10.8.1.1. And that's kind of where, that's most of the configuration. There's a lot of stuff about configuring quality of service that is important, but there's a lot of tutorials online for how to do that. Again, like we were talking about earlier, remember how I was talking about there's this feature called DSCP to Q and not necessarily DSCP to QoS or something like that. And what we're going to do here, just for the sake of argument, is we're going to say 46 goes to 4 and 34 goes to 3. Okay, it's already there. Cool. Got it. So quality of service is set up. IGMP snooping is set up. My VLANs are all set up. Now the only thing I need left is to make sure that my multicast is set up, right? So then I go here. I follow the instructions on Cisco's website, and I click Bridge Multicast Filtering Status, Enable, Apply. Enable, and then I go here, and I'm going to enable it, and apply it. All right. So now I've got my IGMP snooping enabled on that VLAN. I've got my QoS set. I have my VLAN set, and I've made sure that my my green Ethernet is off. And that's most of how you would set up an SG300. Now, I know we're gonna kind of go long here. I do kind of want to set up the Arista, and really quickly, it shouldn't take a whole lot of time, but at least we can see what PTP TrackHound looks like when you have a boundary clock enabled. Do we have time for that?
Sure. And while you're doing that, I saw a question about a cost-efficient boundary clock too. So
Yes.
while we're on boundary clock topics, we'll hit that too.
Yeah. So the most price-efficient boundary clock, I think, is going to be the RTEL one. I can't remember the exact model number, but unfortunately, due to the processing power that is needed to do boundary clock, you end up having to pay for a much more costly, much more robust switch to do this boundary clocking thing. However, I think RTEL, hold on, pretty sure it's RTEL. Quora, there we go. Yeah, so this guy right here is basically one of the cheaper options for, it's like a 1 gig switch. They have a 1 gig and a 10 gig version. And it's not cheap, but it's significantly cheaper than all of the other PTP-v2 boundary clock stuff. So, and then they've got the 10 gig version and the 1 gig version. So that would probably be my suggestion to start looking into if you're looking into a cheaper boundary clock switch. The 10 gig version, I think, has significantly more ports on it. But again, some of the stuff over that, you talk about a Catalyst 9300, which is not impossibly expensive, but it's definitely probably going to be more expensive than this. And then you start to talk about Aristas, which are awesome. I mean, really, really awesome, but man, are they expensive. So, all right, I'm going to go ahead and swap everything over really quickly. If you guys would just bear with me for a moment. All right. Okay. Might take a second for us to load back in. But so what we're going to do, I'm actually connected. Oh, can't do that. Okay. I'm actually connected to this switch via a console cable. And I have cleared the configuration as much as I could, except for one configuration value that allows me to use unsupported transceivers because they're expensive. So what we're going to do to start with is I know that I've connected my stuff on ports 1 through 6. And again, like I said, because there's so many ways to configure so many different switches, I'm not going to really dive really deep into this configuration, but I will show you basically what we're going to do here. So we're going to do an enable command, a configure terminal commands, and this basically what this does is this gets us into a spot where we can enter configuration values for the switch. I'm going to make a VLAN 100 by typing in VLAN 100, and then I'm going to change the interface values of VLAN 100. So go ahead, interface VLAN 100, and then under IP address, I'm going to do IP add 10.10.1.1 to basically coincide with all the current IP addresses that all of these devices have. And then I'm just going to say, because I know my stuff is Ethernet 1 through 6, but I'm just going to do Ethernet 1 through 10 and change it all, and then change those to VLAN 100. So then we're going to put it on VLAN 100. Then we're going to do some commands to enable IGMP snooping and querying. Then we're going to enable boundary clock. And we're going to watch how that works with PTP TrackHound while we're actually doing it. So it'll be kind of interesting. So, all right. So let's do that. So I'm already in enable. So what I'm going to do is not skip the enable part and then go to configure terminal. On an Arista switch, you actually don't even need to do conf t, but you could actually just do conf. And then what I'm going to do is I'm going to make VLAN 100. Okay, so I've got VLAN 100. Then I'm going to change some interface values for VLAN 100. So you'll see that I went to configure interface VLAN 100. Okay, so what I'm going to do here is I'm going to give it an IP address. This is the same exact thing that we did on the Cisco SG300. It's just a little bit different in the terminal.
Can you zoom in a little bit on that window too?
Yes, I think so. Let me. Let me do it in Windows. Is that a little bit better?
Yes, it is.
Yeah.
Okay, cool. All right, so now I'm going to give it an IP address. So IP add 10.10.1.1.255.255.255.0. Done. All right, so that's good. So what's our next step? Our next step, let's look at our little document here. Okay, so now we're going to attach that VLAN to our ports. Okay, so we go here. I'm going to say exit to get back to the configure thing. And then I'm going to say int for interface, Ethernet 1 to 10. Okay, so now I'm configuring Ethernet 1 through 10. Simple as that. And now what I'm going to say is switch port VLAN 100. Now there's a lot of background to this command, but basically all that this means is that I'm going to make these ports part of VLAN 100, and I messed it up. Switch port access VLAN 100 because they're access ports. All right, so we've got that. So now all of our ports are access ports on VLAN 100. So what's next? So let's just test this really quickly because I'm on there, and let's see what we're gonna look at here. So I'm gonna pull up my terminal emulator. I'm gonna ping 10.10.1.101. Hey, I can ping 10.10.101, that 1.101. So that's good. That means I can access that. So let's go to that website really quickly and see what we can see. All right, so we can see all of our stuff, right? So these are all really good things to see. So everything is kind of set up and working at least to some extent. But let's turn PTP on because we can always be better. We can always create a more cohesive network. So I'm going to go end, and then I'm going to go configure again. And actually, before we even do that, we're going to make sure that IGMP is enabled completely. So now, I'm going to do this. This is going to make things so much easier for us, guys. Okay, so I've got IP IGMP snooping, IP IGMP snooping query, IP IGMP snooping query address, and then assigning it specifically to the VLAN. A lot of this stuff has already actually been done for us, but we're going to do it again, basically just to enforce good habits and to make sure that everything is configured correctly. All right. Okay, so that is all done. So if I end and do a show IP IGMP, show IP IGMP snooping, sorry, I'm going to see a bunch of information. I can see that IGMP snooping is enabled. I can see that it's enabled on VLAN 1 and VLAN 100. All right, awesome. Show IP IGMP snooping groups. And I can see all of our IGMP groupings, IGMP snooping groups. So I can see PTP, firmware upgrades, configuration, audio, audio, audio. Good stuff. So now let's take a look at what PTP track count looks like for us. So PTP track count looks very similar to the way that it did. We've got 3 slaves and 1 grandmaster. And I can see that we have an announce rate of 1 second, a sync rate of 8 seconds, and then these guys have a request rate of about 1 second, right? Okay, so conf T. Let's see what happens when we change this over to a boundary clock. So I'm going to say PTP mode boundary interface Ethernet 1 through 10. So we're going to now edit every Ethernet. We're going to do a PTP enable. And we're going to do a PTP announce interval. Now what we're doing here is we're actually telling the switch, this is what I want our announce interval to be. This is what I want our sync interval to be. And this is all defined by those media profiles. So media profile, if you've heard A16, if you've heard AES67 media profile, if you've heard SMPTE 2059-2, those are all profiles with message rates. So I'm going to do this one, interval 0. Now, interval 0 doesn't mean 0. Interval 0 is actually a log second. So the log second is 0 is actually 1 message every second. Oh. And I'm going to do PTP sync interval -3. And interval in -3, again, it's a log second. And -3 in log seconds is 8 messages a second, or 1.25. 0.1.25, but we can't do decimals on switches, so we have to do it this way. So now, if we go back here, we'll notice some stuff that's really interesting. So we've got our grandmaster, which is still our Riedel device. That's our Bolero antenna. You notice we don't have almost any information for it, for announce rate, sync rate, request rate, management device, all that kind of stuff doesn't really exist for this device. But in fact, we don't even know its IP address or its interface. But what we do know is that the Arista is the propagated master of this grandmaster. And we know the IP address of the Arista, and we know a lot of the information coming out of this. We know the announce rate is 1 second and the sync rate is 8 seconds. So this is kind of the difference between what we look like in this versus if I go whoop. And we change this, and now what we're seeing is a little bit different. We're seeing everything again. Now, PTP track count is just an interpreter So it's kind of important to refresh it when stuff kind of goes wonky, and then we'll kind of see everything a little bit better. So it's still trying to figure out all of those messages because it's still trying to turn off IGMP or PTP, but basically we're back to a state where we have one grandmaster, which is 10.10.1.101 and 10.10.1.782, and those messages are being propagated through the system. Strange enough, I don't know why we're seeing the other ones, I think maybe. But alas, this is basically the demonstration between this and that, and how to use PTP track count and what it kind of all looks like. There we go. I bet we just needed to resubscribe to all of it. So anyways, that is that. Okay, so I think that's most of what I have. I see a couple questions that I will answer. I just want to finish up by throwing out these quick tools right here. So the biggest ones are these guys up here. So PTP track count is very important for when you're troubleshooting a 2110 network. Wireshark is very important for troubleshooting a 2110 network. PuTTY is very important for controlling switches and getting to SSHing into things, and command prompt or a terminal emulator. So like obviously I have command prompt here, but I don't typically use it because it doesn't have tabs, and I kind of like this one better, which is called Commander. And basically it just is exactly the same thing. It just looks a little bit better, and I can tab it out. So I can have another tab with another thing. So I can have multiple PuTTY sessions going in the same thing. I had Audacity on here because there is a way to go into Wireshark and take the audio payload and analyze it and export it into an RTP stream and then open it and listen to it. But as we kind of went through this, I felt like that was a little bit extraneous, and maybe if you're interested in that kind of thing, I'm sure we can get together and talk about it. But I see a question on the board right now that says, in a world of live sound, who should be responsible to set up these switches to properly deploy them on the network? Yeah, I mean, it's a tough question, right? Because it would be, ideally, it's not us as audio engineers or video engineers, it's, a network engineer, because we don't, like, our world is in audio and video. But in reality, what I've found is that what we end up having to do is getting to a point where we are both audio engineers and network engineers at some level, because that's kind of the world that we're going to end up like living in, because we, like, at some point, especially with the world like we're living in right now, in order to do live audio from a remote site consistently, like we kind of have to have a basis in networking, or else we're gonna, we're not gonna be able to adapt into that new stuff. That being said, like on large scale live events and stuff like that, I think that for the most part, it's gonna end up falling on our shoulders, just because no one else is gonna want to do it. And with the amount of pressure that comes with that, having an outside person do it and not having control over it, I think it gets dicey very quickly. It's much easier to have control over your own network and deploy your own network than it does to allow people that aren't broadcast centric to control a network. And that's kind of why, like, I think oftentimes we see it taken upon ourselves to become the network / broadcast engineers. Yeah, I think that's just what I think. I'm sure there's many other opinions out there. Yeah. If you guys have any other questions, feel free to shoot them up. I think that other than that, that is it for me. I hope that you guys have had a pretty good time thus far, and I think we went way over our time.
Well, we did, but I did see that question. PTP values for Bolero devices, antennas, belt packs, things like that. Determining those. That was, I think, a last minute question that came in there.
So there's a way to determine that in the UI. That basically is a level between 5. So like right now the offset is between 500 and 1K, or it'll go down to like 100 to 500 that 100 to 500 nanoseconds, or it'll be like less than 100 nanoseconds. What we're looking for, and you'll find this with almost every DECT-based intercom system out there that uses IP, is that we're looking for about a microsecond of offset between master and slave. And this is purely because of the synchronous nature of DECT, and because you need all that together and for those seamless handovers and stuff like that. I think somewhere in the 2110 spec it talks about 1000 nanoseconds or 1 microsecond is good for, is like what is technically required for 2110 devices. However, you can realistically go up to 3000, but you start to see issues when you go up to like 5000 nanoseconds. So that's like 5 microseconds is when you really start seeing issues with non-DECT based applications. But the DECT based stuff, because of DECT and because it has to be so tightly knit in order to do those handovers from antenna to antenna, those end up needing to be a lot closer to 1000 nanoseconds or 1 microsecond.
What would you recommend as the setting for your AES67 card and most of your antennas and your master antenna, just as reference numbers?
So I would, in terms of recommendation, it's tough because it's like, like what we're looking for. But what I can tell you is that when you're in a non-PTP aware switch, what you'll see is that you're anywhere between like 300 or above nanoseconds as a RMS, which is like a mean value, and then your maximum value will be somewhere around like 500 above. But then as you add switches,
the cards default to 124.
Oh, you're okay. Sorry, I understand what you're talking about now.
I'm talking about a different number. Yeah.
Yeah, no, you're good. Okay, yeah, so they do default to that. So, I would recommend most of these default values, but again, it's totally customizable, right? So if you go, whoop, that's not what I'm looking for. I'm looking for this. So yes, the PTP priority, it defaults at 120, but the PTP priority 1 actually is less than any of the Bolero antennas because we never want an AES67 card to take over for a Bolero antenna. The processor and the interface are not as good as the Bolero antennas are. So keeping it on PTP domain 1 is completely fine. Keeping all the PTP priorities the same is totally fine. In a healthy system, you shouldn't need to change the PTP role away from automatic, but in a 2110 system, you will never ever want anything to take over as master. So you might as well put everything to slave anyway. Slave only is.
This is the AES67 card you're looking at now?
This is the AES67 card. So its PTP role is automatic, meaning that it'll select whether it's a master or slave. But I can force it to never.
What about the setting for your antenna?
So the antenna is actually on a net wide. Whoop, my screen is so big. The antenna is on a net wide setting. So by default, the net wide setting is, I don't think I can see it. Oh, the network, sorry, no, it is not on a network setting, net wide setting, the actual, sorry. These values are typically, the default is at 124.
For the antenna.
For the antenna, and you can keep it like that unless you do have a centralized antenna that you're using as a master. In which case, I would recommend putting it down for 1. Yeah, well, actually, it goes down. So if that one's going to be the master, you're going to want it to be 120, or
well, the
less,
cards
more.
were 120.
Right, but their PTP 1, I don't know if we can see it here.
0
was probably a higher number. So this will never actually, in a healthy system, you will never see a card take over as the master. Because remember how I was talking about PTP priority 1 and 2? The PTP priority 1 is like 140, right? So it's something that won't ever be touched versus the PTP priority 2 is 120. So maybe you can set the priority between AES67 cards, but not between an AES67 card and a Bolero antenna.
So if all the rest of your antennas are 124, what would you, if I wanted to make one of them a master, what would I set it for?
123 or lower.
Lower than the individual cards. Okay.
Yeah.
So the automatic, the cards, the AS67 cards, in reality are picking a higher number in the automatic
Yes.
mode.
Yes, you are. But the reason that this works and the reason that 120 is the default value is because PTP priority 1, which is the first thing that the master clock looks at, is much higher. Something else that we can't define here, that we won't allow people to mess with because we don't want people to get into like that. Typically with PTP devices, PTP priority 1 is not customizable, and then PTP priority 2 is. And that way you can, like, manufacturers can say, my clock is really strong, I'm gonna set my PTP priority 1 to super low, as in like more willing to be master, and then my PTP clock is not very good, so I'm gonna set it to something really high so that it doesn't take over as the master. And so that's the case between the AS67 cards and the Bolero.
Would you recommend setting one of the antennas to be a higher priority, or just leave them all the same?
The only reason I would recommend, in the scenario in which I would recommend that, is if you do need a master antenna to be central, because maybe you don't have PTP aware switches and you need a central PTP device so that you're lessening how much space in the network you're going, right? So in that sense, what I would recommend doing is putting one of the antennas, the most central antenna, the one maybe as close to the core switch,
right at the core, right,
to the lowest number. So then I would take this and be like, all right, 120, and then we could do that, but we could also do 120, and then that one, it's going to resync because it's going to change all its priorities, but that's going to make sure that that's the master over top of any other Bolero antennas.
And you said it's important that if you don't have PTP aware switches, this is not going to make any difference because it's not going to affect them, right?
It will. I mean, it won't affect those, but it will affect like it will affect basically sorry, it won't affect the switch, but it will affect the rest of the network. So in a network that is basically completely non-aware, and I have one core switch and 3 external switches, instead of making my master on one of my external switches and then it has to go hop, core, hop, now I want my Bolero antenna to be at the center so that it takes less time for those PTP messages to get to all of my other devices.
Right.
So it doesn't matter, but it doesn't matter to the switches if it's non-PTP aware. So yeah. I see a question. I'm gonna move my little guy over. Hold on. AS67 multicast IP addresses, do we just make up 239 blank 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 numbers, or do you have a suggested format? So Riedel internally, we have what we would consider our internal best practice is to, for Bolero antennas, Bolero belt packs to use 239.255.1. and then the Bolero ID number. But otherwise, it really doesn't matter. The only thing that you need to be cautious of is that you're not stepping on another multicast IP address. So if, say, I went into the switch, and the only thing that I just be careful of is I go into the switch and I go show IP IGMP. You guys still see my screen, right?
Mm-hmm.
Yep.
Okay, cool. Show IP IGMP snooping groups, and I see all my groups. So I see all my groups, I check all my groups out. I don't want to put anything that's going to conflict with these. So the easiest thing to do is just make an entirely new range that doesn't conflict with any of my groups that I have. Does that make sense?
Yeah.
Yep.
Okay.
So
Cool.
yeah, just the first 3 octets would be unique to this, and then the 4th octet would be the ID of the pack.
Sure, yeah, and that's just the best practice. So you can do it any way you want. Just the only thing to be careful of, you can make up any IP address that's honestly in the like 224 onward range almost. But just be careful not to step on other things. Typically we see, but just as a note, typically what we'll see is 239s. Yeah, 239.x.x.x, and you can just make up whatever you want as long as it doesn't step on anything.
In your screen right there, how did you log on to the local host? Did you just go to?
When you boot up this switch,
Are you on the switch now or just on the network?
I'm
with
on
a
the
terminal?
switch. I'm on the switch. The
Okay.
switch just happens to be called localhost because I cleared the configuration. And I'm going to clear this so that it doesn't look so. There you go. Okay, so this is what it looks like when you log into like an Arista switch. You just says localhost login, so that's the host name, and so I say admin, and there's not a password because I just reset the switch. And if I wanted to change the host name from localhost to something else, I'd just be like enable. And now the switch's name is different. So yep, there we go.
Wow.
So yeah, that is that.
Nice.
So
I can't type that fast.
wow.
I do a
He
lot
has
of typing.
an accelerator on his fingers or
I'm
something.
telling you, I will tell you the one thing I did do after when we were talking just prior to the, I bought one of those Network Plus training sessions for $16.
Yeah.
Because I was like, you know what, for $16,
Not so bad.
you know, and you know, obviously this is extremely advanced. I'll be the first to admit that. But I think also, you know, we've talked about this 4 weeks ago. There's going to be a lot of people that exit this this break doing something different in our industry than what they came in doing. And I think they'll be better for it. And I think networking is one of those areas that frankly, I think we're going to have a little more time on our hands. And this is something we need to learn. Now obviously, Steven's, you know, at the far end of the spectrum, right, in terms of the capabilities. So, dude, I'll tell you, I was quite impressed. I mean, the typing alone in but that's part of the, you know, I would suggest that, you know, the CCNA, for those of you who may not need that level, start with Network Plus. Get that, because the more we understand about how our networks are working, that's what's, I think, so much different. You know, it used to be that the skill was learning to solder, and then the skill was learning to take proper electrical measurements, and then you did, and what we saw with 2110 is everything's converged now, and this switch is it, right? I mean, I already sent out a bunch of notes going, hey, we're going to need some more switch talks, right? You know, especially around Bolero, you know, they're just become hyper focused almost in some ways that we wouldn't normally have those discussions, because the systems are going to grow bigger. They're going to grow larger, whether wired and wireless. Everything is going to be transiting that switch. And, you know, like the boundary clock discussion. I remember when we were just happy to talk about word clock and Big Ben's, and we're like, who's going to be the master, right? And now, you know, that didn't have a telnet jack in the front, so it seemed pretty straightforward, right? But I appreciate everybody that's held on here. We had a pretty good number that held on to the very end.
Yeah.
And you know, it's kind of like that fire hose just had more and more water coming out of it, and everybody was just holding it. And thanks, Stephen. We'll no doubt, you know, be talking with Rick and coming up with more opportunities to connect, probably really focusing down. I would suggest anybody that's still on right now, send some notes to us about how you would like to start parsing out the network. Because like I said, I think we're going to have time, and we need to understand, and maybe the understanding needs to come along with each of these segments that we're doing. So, any notes, Mac, Pete?
Oh, not me. No.
No, that was really great, Rick. I loved it.
Stephen, you win for longest presentation.
They-
No
Oh,
breaks.
good.
Nice. I mean, even with the camera clicked off, I'm still going to give you the award.
All right.
So thanks everybody for joining in, and please send in your notes. I saw a few that came in during this. We're open to trying to facilitate any kind of discussions that will connect with people. So on these topics. So
And,
I guess
and
until we meet
any
again,
topic,
go ahead, Mick.
any topic that will further anyone's usability once they get out into the world again.
Yeah,
I mean,
exactly.
when we go back to work, we may be working differently, and we should have as many skills as we can.
Yep. Yep, exactly. So that we will continue talking, and Stephen, you'll probably be getting a few emails once everybody's back behind their gear, and lucky you. So
That'd be great.
have a great night, everybody. So
Thank
long.
you. Good night, everybody.
All right, bye.
Bye-bye.